Hello, everyone. I hope you can hear me okay. Thank you very much for joining us. It's great to have such an amazing response, have so many people join, and I hope you find today's session useful and informative. We have 15 speakers from, I think, 8 different countries. And they'll be talking about a wide diversity of topics related to the applications of nighttime satellite imagery. This event came about because Alba Orbital started looking into nighttime satellite imagery around 2 years ago, and we found that while there are many people doing lots of amazing things with nighttime satellite imagery, that there wasn't really any sense of community in no kind of single event bringing everyone using this type of data together. So we thought we'd create an event like this, and we'll see how it goes. And hopefully, like I say, you'll find it useful, and it's something we can continue in the future. Our first speaker is Maya Bennett from the University of Hong Kong, and I'm just going to add Maya in now, so hopefully she can share her screen. Hi, Maya.
Hi, it's Mia. Thanks so much for the opportunity to speak today and for the introduction. So I'll just go ahead and share my screen. Let me see.
Yep, hopefully you can share. Okay.
I'm actually not. Oh, here it is. Okay.
You can. Go.
Got it. Okay.
That's it.
This bigger. Just start my. Okay, great. So thanks once again for the introduction, and hi, it is really nice to be a part of this virtual community, and hopefully we can all meet in person in real life sometime. But today I'll be speaking about my research with Dr. Hilary Faxon, a postdoc at UC Berkeley. She can't join today due to the time difference, so I'll try and do justice to this work. She's really critical to it because she is the expert on Myanmar. Having done a lot of field work there. So with this project, what we tried to do is integrate my background in using geopolitical or geospatial data within a kind of critical political geography framework with her really rich ethnographic work from 3 years of research in the country. So today I'll just walk through Myanmar's political geography. I'll talk about the methodology we've employed, which involves critical remote sensing. So I'll describe that framework, which is really trying to bring together rigorous remote sensing skills within this more critical framework and applying that kind of theory to pay attention to issues of uneven development and issues of injustice, particularly. Then we'll just demonstrate how nightlights can be used as a proxy to estimate development and how we've done that in Myanmar at different scales, looking at different regions within the country, and then crucially, looking at Myanmar's borderlands, specifically through hotspots of development. So with this work, we use both the DMSP OLS dataset to go back to the early 90s, and then the VIIRS data to have a more contemporary look in the past 5-10 years or so. So Myanmar today, just to give you an overview of the country, it's in Southeast Asia. It has a really quite sizable population, 54 million people. And the country, as you may be familiar, for better or worse, is highly ethnically divided. The country's ethnic majority of the Baman people are concentrated in the central region. So Myanmar is divided into states and regions. And then the more, the various ethnic minorities tend to be concentrated in the peripheral states that border Myanmar's 5 neighbors of China, Thailand, Laos, India, and Bangladesh. The one ethnic minority which has the highest profile may be the Rohingya, who have been persecuted by the government and the military for quite a few decades, but very much more so in the past few years. So the Rohingya people have fled to Bangladesh just across the border. So we look at these ethnic divisions and how those affect development and what can be seen from space with regard to these different groups' welfare. Myanmar is also a very resource-rich country, which makes it very lucrative for all of its neighbors to try and get involved and try and get a piece of that pie. It has timber, metals, and rare earths. In fact, it's the world's largest tin producer, which only happened in the past decade or so, which is a really quite impressive phenomenon in a way. Also exports natural gas and opium and other drugs. So there's a lot of illicit trade going on, which also makes the country particularly interesting for nightlights and satellite observations in general, because there's so much that's not being reported in official statistics, and that may even be hard to find out on the ground. So satellites can provide a sort of other lens into those phenomena. And then, of course, Myanmar has been in the news in recent weeks, right? It's very politically unstable. The military has carried out a coup. So there's protests and internet blackouts going on right now. So all the more reason to try and triangulate what's happening with as many sources of data from above and on the ground as possible. So what can critical remote sensing offer that would go beyond what a maybe more typical remote sensing approach would do? With critical remote sensing, as political geographers, both of us are deliberately trying to apply the same skills and tool sets that a remote sensing scientist might do, but within a framework that's much more attentive to the politics of satellites and the data they produce, understanding that these images can be used to highlight certain phenomena and downplay others. I think that kind of process and instrumentalization, if you will, of satellite data was very much clear in the war in Iraq, for instance. So underscoring, first of all, the politics of satellites and the imagery. Second, we actively use the data to push back against some of the narratives that governments might put forward. For instance, the Myanmar government is often celebrating the increase in connectivity and trade with its neighbors. But we want to scrutinize that and even see if it's possible to contest the economic statistics that the Myanmar government may be publishing to that effect. So we are very attentive to processes of uneven development, and particularly which groups of people may be getting left out of these larger statistics of GDP growth and cross-border trade. And then with critical remote sensing, we also try and iterate and go back and forth between this view from above that satellites can importantly provide by enriching and contextualizing that data and those pixels with on-the-ground fieldwork, as Hilary's been doing, and also by kind of situating this data within a more kind of a more attuned, I guess, perspective on what's actually happening with a real kind of local knowledge of Myanmar in this case. And some of these ideas I've explored before in an article in Political Geography, if you're interested. So I think a lot of this, the fact that nightlight imagery can be a really reliable proxy for socioeconomic activity, meaning we can estimate all sorts of processes and anthropogenic processes ranging from population to GDP, even infrastructure, although this gets a little bit tricky. I think a lot of these ideas will be familiar given the other presenters here. But I would just emphasize here that one thing nightlight imagery has a lot of potential for is making estimates in places where there are potentially very inaccurate government statistics or where they are altogether lacking. So Myanmar is one place where this would be quite promising. Some limitations, which I'll return to at the end, are that activities that are not very well lit obviously won't appear in this type of imagery. And that's something that ends up resulting often in the kind of lack of, I guess, the inability of this type of imagery to kind of shed light on what's going on with, for instance, really rural, impoverished people who don't have connections to power grids. We're not really going to be able to understand what's going on with those populations with this data. It just won't be able to tell us that. So that's something I'll return to, which is particularly, I think, important for thinking about these ethnic minorities on Myanmar's periphery. So Just drawing on another previous paper I wrote here, just to give you an insight into how we can use nightlight imagery to not only look at phenomena within the boundaries of nation states, which I think tends to be the way that this data does get processed and analyzed, we can importantly look across these borders. And this is an example from Syria with VIIRS imagery, which is very high resolution, a 750 meter resolution here. We can see that just in 2 years during the Syria civil war, all of these lights that surrounded a highway that connected Syria to Iraq completely disappeared. And instead, southern Turkey brightens a lot. So this is where a lot of refugees from Syria were headed. So we can really use this type of data to provide insights into cross-border phenomena, not just looking at processes scaled within a given country. And so that was one driver of our desire to want to examine Myanmar's borders in more detail. So we look at this data across political borders. We use the DMSP OLS harmonized dataset that was published recently by 2 scholars in Nature. And then we compare that with some of the VIIRS imagery. The harmonized dataset does go into 2018, but we weren't able to use it accurately because I think in very rural areas, the harmonized composites are not that useful in those areas. And then we kind of go back and forth and look at Google Earth imagery to get a higher resolution daytime view into some of these sites. And then we have administrative boundaries to look at the different regions and states and the borders that Myanmar shares. And then, as I mentioned, here's some pictures of Hillary doing fieldwork over the course of 3 years. So moving into the results and discussions. So this is on the right, a change detection map of Myanmar between 1992 and 2013. So the full breadth of the DMSP OLS data. And what we can see is that Myanmar is a lot darker than almost all of its neighbors except Laos, which is perhaps even more rural and impoverished. So if we were to go in and then assemble that data into the kind of the 16 or so states versus regions, we can see there's a clear disparity in that ethnic majority lowland regions where the Bamon people live are actually 5 times brighter per kilometer squared than the ethnic minority states. And you can see that even within Myanmar, a lot of the lights are concentrated up and down in the middle where the main cities and infrastructural corridors lie. That being said, nighttime lights in ethnic minority states did increase more quickly, which might suggest they're undergoing more rapid development. We also noticed that there's exponential growth in the new capital of Naypyidaw, which was a kind of contrived capital that the government decided to just put smack dab in the middle of Myanmar in 2002. And you can see in Google Earth imagery, it really just transformed overnight, sucking up a lot of the kind of growth from neighboring states. So, and then with the borderlands, this was quite interesting, and this is where a lot of our attention focused in our analysis. Is basically what we did here was we took a 25-kilometer wide kind of frontier along the interior of Myanmar and then compared it to the 25 wide kilometer frontier on the other side, so spanning through those 5 countries, those 5 neighbors. And if we were to total all of the lights in the interior versus foreign borderlands of Myanmar, we determined that Myanmar's interior borderland is only 11% as bright on average as the frontier across the border. So that suggests, as you can see here in this VIIRS tritemporal composite, where red lights are more recent bright lights and blue ones were brighter a little bit earlier on in the period, what you can see is that really there's development happening in Myanmar's 5 neighbors and 4 of its 5 neighbors running up all the way to the border. But that is not really being mirrored in Myanmar. So that suggests that even though trade may be increasing between Myanmar and its neighbors, it's not taking the form of infrastructure development that's visible from space. And instead, it might point to a real extraction of resources in Myanmar without any added value coming in. And this may be occurring as a result of a kind of encroachment and extractive processes being led by its neighbors. And so I'll just walk through a couple of examples. We used the hotspot tool in ArcGIS to kind of drill down into where these the kind of statistically significant brightest concentrations of lights lie. And you can really see that these are over a 6-year period just tend to be concentrated in China and Thailand. So that might be where the most lights are happening, and also maybe the most trade and various forms of extraction, both legal and illicit. And so what was also interesting is that if you were to look even more closely at these hotspots, almost all of them fall on the foreign side of the border, and they're very rarely on the Myanmar side. And so we are able to look at this in 3 places in particular. So we look in China, on the border with China, Thailand, and then Bangladesh. And so with China, this was perhaps one of the few instances where lights in Myanmar, where the hotspots, if you will, were actually on the Myanmar side. And so what these hotspots on the Myanmar side reflect is interesting, because this is a part of Myanmar that's actually controlled by the United Wa State Army, which is the kind of breakaway faction that represents the Wa people, who are more ethnically Chinese, often speak Chinese language. And I think with this phenomenon, where you even see here the kind of town is very bright on the Myanmar side, this is a real kind of hub for all sorts of illegal trade of tin and opium and wildlife products. The one in the middle is interesting because this is a new housing development being led by the United Wa State Army. And I think this might suggest that perhaps these militias and armies, which are, I think, often in the media thought of as these almost evil forces, actually can provide infrastructure development sometimes, maybe arguably in a more effective manner than the government, especially in these peripheral regions. So a process certainly that merits further thinking through. Looking at the case of Thailand, this is one other instance where there's some lights that we noticed are increasing on the Myanmar side, but you can see in the top right here, they're almost still all concentrated in Thailand. There has been more and more infrastructure development here, but it still seems very unequal, and it seems like maybe a lot of that activity is ending up draining into Thailand, which maybe is really kind of benefiting from this enhanced connectivity, which is now taking the form of a new Asian highway that will go all the way to India. So Myanmar is getting more and more connected, but it's not necessarily getting brighter. Now, the last kind of vignette here to highlight is the most tragic one, and this involves the single set of hotspots around Bangladesh, the Bangladesh-Myanmar border. And again, as you see in the second picture here, all of those hotspots are concentrated on the Bangladesh side. But what they are pointing to is not any form of, necessarily long-term infrastructure development, but rather the establishment of the world's largest refugee settlement. So some 700,000 Rohingya refugees have fled from Rakhine State into Bangladesh in the past 4 or 5 years or so. And other research published in various remote sensing journals has attested to the fact that there's also been a lot of deforestation going on, which you can see in Google Earth and other daytime satellite imagery. So I just want to move to the end here, since time is coming up, and just return to my point about some of the limitations of nightlight data. I think often with satellite imagery, it's thought that they can see everything, they can perhaps potentially solve everything because they are so omniscient, but there are many things that they cannot see. And so one of these things is often massacres of people who never lived in illuminated houses to begin with. And this work has been done, this kind of satellite imagery using Google Earth and other optical daytime imagery has been done by various think tanks and nonprofits, which pointed to in a really terrible massacre of people in the village of Tulatoli in August 2017 as part of this ongoing genocide. And you can see how this village along the river in the middle figure is actually entirely burned to the ground, and in fact has now grown back as basically kind of just vegetation. If we were to look at this with the nighttime light imagery, there's basically no difference. So imagine if you had no idea that this was ever an issue, this massacre, it would look as if nothing had happened in the nightlight data. So I think this just points to the fact that we really need to kind of, in doing critical remote sensing, try and triangulate between both on the ground and satellite views to get the full picture of what's going on. So to conclude here, we detect rapid brightening of this kind of black hole during the earlier reform period in Myanmar. But some of the new brightening that we notice in the country is starting to reproduce various spatial and ethnic patterns of uneven development. Some exceptions, though, might be in areas which are not necessarily controlled by the government, but rather by some of these kind of breakaway autonomous governments and armies. Also, Myanmar is still much dimmer than its neighbors, despite the government starting to trumpet this increase in connectivity. So, only 11% as bright on average as the rest of the region is a massive disparity. Lastly here, a critical remote sensing framework that ground truths geospatial data with ethnographic and qualitative observations, I think is important in that it can reveal these trajectories of resource extraction, cross-border trade, and forced migration, and force us to think harder about questions of social and spatial justice. So I'll leave it there, and I think there's a minute or so for questions. Thanks so much for listening.
All right, thank you very much, Mia. That was very, very interesting. We just have one question, and it's from Jay Lee, and he's asked, do you find any abrupt change during 2011 to 2013 because of the inconsistency between the DMSP and VERS images, although the dataset is so-called harmonized dataset?
Yeah, thank you, Xi. So in the research, we stuck with the DMSP composites from 1992 all the way to 2013. We looked at the kind of simulated, I think the simulated DMS composite for based on the VERS data from starting in 2011 and then looking all the way up to 2018, and we did see a big jump that cannot be attributed to sudden development. So in the end, that's why we had to break up the data, and we found that the harmonized data set was not comparable within itself for the case of Myanmar. So those simulated composites were not working out. And I think in the paper, right, it's saying that in places where the digital number might be lower than 30, it will be a little bit more difficult to have this kind of more fluid seamless analysis, and we did find that to be the case, regrettably. So, but still a really exciting data set, really useful.
Great, and one more just in from Jan Peter Muller. He's asked, would a higher spatial temporal resolution improve tracking of fires?
Yeah, that's a great question. So we had to confine the VERS analysis. We chose to look at it in the month of December because that's the time when the fires are least prevalent, but it's also the least cloudy, kind of combining those two. And so I think if we had I don't know if it's so much about the higher spatio-temporal resolution for fires. I mean, I didn't look at it too much, but I do know that fires in and of themselves are an issue for trying to track development, right? Because they just are interference. So if we could maybe track them better, then we could create a fire mask, perhaps more carefully, that we could apply to further analysis, I think.
All right. And one more as well, just then, Lewis Miller's asked if you can expand upon your comments regarding correlating visible light emissions with thermal or NIR and SWIR wavelengths, which can help with industrial processes or land use changes, including the non-illuminated areas you mentioned.
Sorry, let me just read through this.
Yeah.
Oh, great. Okay, so this is not, I think this is an important comment. It's not something that we have looked at yet, but I do think that given all of the incredible research being done on Myanmar with regard to deforestation, for instance, and those researchers using the other wavelengths you mentioned, I think it would be really interesting to collaborate and think about how our research, which is more focused on socio-political phenomena, socioeconomic phenomena, could be really tied up with, I think, a lot of the ecological transformations that are going on, and I think that are not inseparable in any way from these various ongoings in Myanmar. So it'd be great to bring in more types of remote sensing data to the process that we're doing, which is mostly nightlight imagery and then Google Earth or Landsat.
Perfect. Thank you very much for joining us, Mia. It was great to have you.
Thanks so much.
And yeah, hopefully I'm sure everyone found that very informative. And we're going to move on now to Jay Lee from Wuhan University. Thanks, Meth. Hello, G. I think you are muted just now, and you should be able to unmute.
Okay. Okay. Thank you, everyone. Thank you for the hosting this workshop. I'm Li from the Wuhan University. So my talk today is monitoring the hourly dynamic of nighttime light using an UAV. I come from Wuhan University, and my institute is the name is State Key Laboratory for Information Engineering in Surveying, Mapping, and Remote Sensing. So, sorry. So my talk will include five sections. First is about the motivation of this study. As we know, the satellite imagery has been used for mapping city light at night in different research fields. So this is DMSP images at global scale. And other images including the views, also some image like International Space Station or the Loja #1 satellite from my university have also played a very important role for the city light mapping. However, although I have been in this research field for many years, I find that the coarse resolution and the relatively fixed overpass time of satellites have hindered fully understanding of the nighttime light. For example, some questions may be not answered by the satellite imagery. The first is how land use contribute to the nighttime light intensity, because you know that the land use is highly spatially heterogeneous, but the spatial resolution of the satellite images such as DMSP is more than 1 kilometer. The second is how land use contribute to the nighttime light colors. Yeah, this is also cannot be answered by DMSP or the views images. Also, how the light of the different land uses change during the night, because you know that for most of satellite only visit one place for one night or even many nights. So it's very difficult to know how the light change during a night. So under this background, I find the UAV may be an potential tool, because the UAV have been widely used in daytime remote sensing and have potential for nighttime remote sensing because of the following reasons. The first is the flight time is flexible, because you can use the UAV to record the city lights of a place for any time, like in both daytime and any time in the night. The second is atmosphere effect is relatively minor, as the flight height is very low, because it's normally lower than the 500 meters. The third is the spatial resolution is very high. For Dajiang satellite UAV, is if the flying height is like 500 meters or 300 meters, the resolution is about 1 centimeter, so it's very high. The final reason is the flight cost is very low, because you don't have to pay any data cost, yeah, for the flight. The only thing you have to spend is labor. So these advantages may help to solve the above mentioned problems in the last slide. So in this research, to test the potential of UAV, to surveying and mapping the city light at night, we employed Dajiang Phantom 4 RTK UAV. The study area is located in the Wuhan University campus, and the detailed information for this location is Faculty of Information Science. The area is about 0.38 kilometer squares, and the urban functions are also mapped through the fieldwork in the right. Yeah. So this is daytime imagery recorded by the UAV. This is our flighting route. And we use 10 flights to map the city lights in the research areas during about 8 p.m. in the 15 April 2019 to the next day, and the time is 5 a.m. So for each two flights, the interval time is about 1 hour. So you can say that we use a UAV to map the hourly nighttime light dynamics. So this is a video that is showing how the UAV works in the research areas. Okay. So in addition to the UAV we also employed the 3 SQM, which the full name is sky quality meters. Although these tools are always used to map the sky brightness, it can also play an important role to record the brightness of the ground or any other target. So the 3 SQM are located. One is for the upwards, and upward in the to record the sky brightness, and also second one is located to measure the temporal dynamic of. I'm sorry, to the dynamic of the ground brightness. And the one is located to measure the spatial distribution of the light from the ground. So we use the photogrammetry software to generate image mosaics for the 10 flights. So we can say that the first hourly temporal resolution image of the city lights were generated by our UAV data. Yeah, so this is the flash. So firstly, the SQM1, which is a moving downward SQM measurement, has shown a very good correlation with that of the UAV images. We can see that for the red band, green band, and blue band, all the correlation between the UAV measurement and the SQM measurement is more than 0.6 in the R-squares for the linear regressions. And also the regression R-square is also high, more than 0.7 for the brightness of the UAV. But it's very interesting to find that the green band has a higher correlation than other bands with the UAV image. So we find that SQM has have a spectral response in the peak for the green band. So that can explain why the UAV green band is more consistent with to the SQM measurement. So both the measurement from the SQM2 and SQM3 showing that a strong correlation with the UAV images in time series. The result indicates that, for example, the SQM measurement, which record the ground brightness, has a R-square in the linear regression of more than 0.98. Yeah. So also the measurement that records sky brightness has a very high correlation with that of UAV. The correlation is also more than 0.96. Yeah. So this result shows that the UAV is capable to measurement the light at night in both spatial and temporal dimensions. So we also use a land use map to overlay with time series UAV images. We find that the night light presented a continuous decline from the 8 p.m. to 4 a.m., losing more than 60% of the total brightness during the period. And also the largest decline in nighttime took place during the 9 to 10 p.m. Also, the pattern of the light dynamic varied among different urban function classes. For example, the outdoor sport field, indoor sport field, commercial and residential lost more than 90% of the lights during the 8 p.m. to the 5 a.m. This is a figure to show the percentage of brightness loss between the 8 p.m. to the 4 a.m. We also used some statistic to map the light off time. This map is the map to show the pixels that with the time of the pixels that with the largest nighttime lamp decline. So different colors to denote different light off time. So for example, the red area is a tennis court, which was turn off lighting between the 8 p.m. to 9 p.m. So this is the case. And the blue area is also a case that's showing the nighttime change between the 4 and 5 a.m., which is a club or which is a bar. For the color analysis, we also find that the blue band had a more relative change during the 8 p.m. to the 5 a.m. The major road is much less blue during the period, and only commercial, residential, major road, and open ground are less blue. This is a map to show this is a figure to show the relative spectral ratio of the blue band. Some of the urban functions are become less blue. Yeah. So why? Also, if you can take some details to look at the image with a side view, we can see that this image is in the major road that where the LED lights is turned on in the 8 p.m. So the major road is include some blue lights from the LED lights, but in the 4 a.m. the LED lights in the nearing commercial buildings was turned off. So that's why we can say the blue light is distinguishing during that time. So we can say the major road is becoming much less blue. Also, this is a case to show how the side view of the UAV is capable to provide more information of the city lights. This is a nightclub. Also, from this image, because this is the vertical observations, the spatial details information are not is not shown in this image. But we can, if we can observe it with a side view, we can see that the door or gate of the window of the buildings is clearly by the side view. So we can give some conclusions. But firstly, UAV is a powerful tool to record the nighttime light. The UAV acquired images were consistent with ground measurement. The second point is the analysis on the UAV images indicate that the city light is highly dynamic and complex in both spatial and temporal dimensions. Because this is the case study, so we can say that the patterns we find in these studies may vary from one location to another. So the only conclusion we can say for the patterns is highly dynamic in both spatial and temporal dimensions. Also, the side views will provide more information on the observation of the light. So our group is still working on UAV observations with side views. I think we will publish a paper on that. So this work is summarized in one paper published in Remote Sensing of Environment in the last year. Okay, thank you very much. So I'm happy to answer any questions from the audience. Thank you.
All right, thank you very much, G. We have one question so far. Christopher Kyba asks, which software was used for the mosaicing?
Oh, okay. We evaluate that the many software is working for this work for mosaicing the nighttime light image. The software we used is a software developed by our lab. The English name is GodWork, but it's not. It didn't open in international market, so it's not a thing. But as far as we know, some famous softwares in international markets, such as Pixel 4D, is also workable for this work. Thank you.
All right, thank you. And one more from Paul. He has asked, could you please tell us about the camera or sensor that you used on the UAV?
I'm sorry, can you speak again? Thank you.
To tell us about the camera or sensor that you used on the UAV.
Okay. The camera we used is a very normal RGB cameras that was embedded in the Dajiang UAV. So we didn't use any individual cameras from some special brand. This is a Dajiang made UAV cameras that was embedded in the in the UAV. But I'm sure that if we can use high quality cameras, we can get a more higher quality images.
All right, perfect. I think that is all the questions we have for you. So thank you very much for joining us.
Thank you.
Thank you.
Hi.
Okay.
Can you hear me?
Yes, we can hear you. Lou, thank you very much for joining us. And
okay, I will share my screen.
Yep.
Okay. Can you see that?
I think it is just. Yep, we can see that.
Is it quick? Okay. 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 Let's begin it. Thank you. I'm very glad to attend this NightLight workshop and meet so many experts around the world. My name is Liu Yang. I come from Wuhan University of China. Our team focus on analyzing the nightlight image on fish activities. So today I would like to introduce one of our work, distinguishing multiple ocean-going fishing boats in the Northwest Pacific Ocean using nightlight image and AIS data. My presentation have 4 parts. Firstly, I will briefly introduce fisheries resource in the Northwest Pacific Ocean. This region is one of the most productive fishing ground in the world because it has the unique geographical conditions and the oceanographic properties. Here is the intersection of the Oyashiro current and the Kuroshiro current. So in recent year, the capture production of this region has reached 20 million tons, accounting for 20% of the total mining fish production of the world. And in the West Pacific Ocean, the Pacific Sauri, Neo flying squid, and champ mackerel are the major commercial fish species. Currently, these fisheries resources are being explored by China, Japan, Korea, Russia, Chinese Taipei, and Vanuatu. The main fishing method is using the light trapping. For example, this is the Pacific Sauri fishing boat here, and this is the night. In the night, there are a lot of light around this boat. So most Sauri fishing boats attracting and gathering Pacific Sauri with strong red light in the night. So this figure is the real picture photoed by my students. They are going on board to the institute survey. So after opening the red light, we can see in the ocean surface there are a lot of many Pacific Sauri near around the ship. So the production fluctuates every year, and the maximum can reach the 620,000 tons. Recently, it has been discussed to subject to quota management by NPFC. Therefore, monitoring multi-nightlight fishing boat plays an important role in protecting and utilizing fisheries resources, and also monitor illegal and unreported and unregulated fishing, and tracking the variation of the fishing ground. From the 1970s, the development of satellite has provided effective detection method of identifying nightlight fishing boat. The ISNPP carried on visible infrared imaging radiator suit was launched in 2011, which has the day-night bond with the ability of the low light detection. So the advantage of DNB image using for fishing activity, including the they can cover the fishing time very same at the midnight, and also they can provide the daily global coverage and also the near real time. So that's a very useful data source. So how to distinguish Sauri boat from the multi-ocean-going fishing boat? We use two sources. One is the visible infrared imaging radiator suit boat detection. We call it VBD. Another is the automatic identification system, AIS, boat detection. We call it ABD. So with the advantage of the nightlight fishing boat identification and the extraction technology, the DNB remote sensing data was increasingly utilized in various fisheries researches. On the other hand, the AIS data was also originally designed to communicate and the boat identity. So compared to the DNB, the AIS data are not affected by weather, and the main information of the fishing boat contained in the AIS data. But AIS data also have some shortcomings, including the incomplete coverage and error in maritime mobile service identity, and also the missing data and deliberate suspension of signal transmission. So our objective is to develop an approach to distinguish the multi-fish species in the high seas of the Northwest Pacific using the ABD and the BBD, and also to create a comprehensive field nightlight fishing boat database that can combine the advantages of both BBD and ABD for multi-species visual detection. So this is the flowchart of the AIS data processing. I will simply to introduce. The first step is to select the target boat from the NPFC visual list. The next step is to sort fishing boat according to their visual type and the target species. And the final step is to distinguish the daily ABD from the AIS fishing effort data. The daily fishing position of the mackerel, sorry, and squid boat was selected based on the based on this MMSI matched with the NPFC list. Another is the VBD processing. So for each DMB images, the image pre-processing under the GLC, geometric correction, noise reduction, and radiance amplification. And according to the daily multi-ABD dataset, appropriate the thresholds were chosen separately in multi-BBD. To determine the range of the multiple BBD, also we use the focal statistic tool to calculate the largest SMI of the pixels within a specified neighborhood. Also, we use the ship radar image for the verification. Okay, let's see the result. This is the original AIS point, and this is our process by using the ABD processing method. We can see the blue is the squid boat, and the red color is the sorry boat, and this green point is the mackerel boat. So we can divide the three species from the AIS data. And another is from the VBD. This is the nightlight image in this region in September 17th, 2018. So we can see there are a lot of group nightlight fishing. So from our approach, we can divide into the, for example, this red is the sorry boat group. The green group is the squid fishing boat, and the blue one is the mackerel fishing boat. So this is the result, and then we process all daily number of the detected sorry VBD and the ABD data. So the blue one is the VBD from the nightlight image, and the orange one is the ABD from the AIS data. So we can see the number of the species specific fishing fleet detected using the VBD approach was larger than the ABD. And then we create the field nightlight fishing boat dataset combined with the VBD and the ABD. So the final result, we can see we can get a lot of information from the final result. For example, we can know the fishing period is from the May 5th until the November 27. And also the period of the increasing fishing number is from May 5th until the September 4th. And also the most fishing period is during the August 14 until the November 18. This is very useful data. And we also process the monthly result. We can see the spatial distribution of the fishing boat in this region. And also we processed the trajectories. From the trajectories, we can see the salary fishing boat from the May to July is they are going to the north. And from the August to November, they are going to the southwest. So that's we can know the whole situation in this region. Okay, the conclusion is our study proposed and developed a method to distinguish and monitor nightlight fishing boat targeting multi-fisheries in the Northwest Pacific using AIS and the DMB. And we think this approach can also provide a reference for identification of nightlight fishing boat in other oceans. Okay, thank you for listening. We wish this year the world will go to the normal and everybody can visit Qingdao. We are in Qingdao, very beautiful city. Thank you so much.
All right, thank you very much, Yang. That was very, very interesting. I am just waiting to see if we have any questions. So for everyone watching, you can ask questions via Q&A, via the chat, or you can also raise your hand as well, and we can let you ask a question via video. I think we have one raised hand. Let me see. Oh no, it's when the hand has went back down. So no questions for you, I don't think. But yes, thank you very much for joining. It's very, very great to see.
Okay, thank you so much.
Oh, sorry, one question actually. Are there any specific colors used for different species, and are these distinguishable with birds?
We are not by colors, but we use by the value of the thresholds. So, but there are also some, because we go to the in situ shape. Some shape have different color. That's true. So we will next in the next research we will analyze the different colors impact.
Perfect, thank you. And one more question. George asked, where do you get your AIS data from?
AIS data. Some is from the free download. We can get some free data, but some is from the from the Chinese government. We have the AIS system.
Okay, perfect. And one more question. Is the resolution of the DMB, sorry, day night band an issue, or are the boats far enough away from each other that you can easily identify them without problem?
Yeah, we think the NPP dataset has enough spatial resolution for detect the ocean-going fishing boat, because the spatial resolution nearly 700 meter, so that's enough. No problem.
Cool, perfect. Thank you very much for joining us, Yang. It's great to have you.
Thank you.
Okay, next we have Giacomo Falchetta from FEEM, Italy, and he's been added in now. Hello, Giacomo.
Hello. Hi. Can you hear me? Yes?
Yeah, we can hear you. If you...
Okay, I will share my screen. Okay, great. First of all, thank you very much for organizing this event. It's really interesting and nice to be involved and exposed to different people researching different topics with a common data and methodology. Today, I'm going to introduce you to a piece of work which has been published, but it's still ongoing, which relates to the use of nighttime light data to evaluate the recent progress in electricity access. It's a joint work carried out at FEEM in Italy and at IASA, the International Institute for Applied System Analysis in Austria. So as you might know, the SDG 7 of the United Nations foresees that by 2030, everybody should be able to gain access to affordable, reliable, and sustainable modern energy for all, because this has very strong interconnections with development objectives. However, as of today, the global population without electricity access, according to the official statistics, stands at about 750 million people, and nearly 600 million of those are located in the Sub-Saharan African region, where there are even 15 countries with electrification level below 25%. And some progress have been reported in recent years, but also recently an investment slowdown in electrification has been reported as a result of the COVID pandemic. Concerning the global electricity access data, there are a number of initiatives led by national and international organizations, such as the World Bank, ISMAP, the United Nations, which try to routinely give an updated picture of the global situation at the country level, also thanks with the direct contact with the government. However, these type of statistics tend to rely on nationally reported electrification levels, which often differ in definition and estimation methods by the government, and surveys on the ground, which are not regular and costly to carry out. And moreover, they rarely report the sub-national heterogeneity sub-country scale. So it doesn't really give a picture of the inequality within countries. And finally, so far, this information has been really scarce when it comes to power consumption or reliability of the electrical supply. Although the ESMAP has recently launched an initiative to collect much more granular and detailed data on energy access, which is a big step forward, but still a few countries have been surveyed and made available. Here, what we propose is to create an open source, updatable, high resolution data set, which improves and helps to keep track of electricity access and its quality, basically to support the production of some more rapid statistics and improve the modeling of electrification and the understanding of the links between electricity access and other socioeconomic outcomes. We seek to create a data set which is based on updated sources, so it can be always recent and be open access and replicable. And we do this in the Google Earth Engine web cloud computing platform, which allows everybody to reproduce it, even if it's very heavy data processing continent scale, which on a laptop would be very challenging. And then we carry out an analysis of this data set to understand the ongoing dynamics. We rely on the virus DMB monthly composite in terms of nighttime lights with about 450-meter resolution. We overlay it with the high resolution settlement layer population, which is a population raster available for all African countries with a 30-meter resolution, so very high resolution. And with the European Commission GHS settlement type, which allows to distinguish between the different types of settlements. And we complement the analysis with the administrative layers and a very broad range of statistics, such as the DHS surveys, as discussed in the previous presentation, the World Bank statistics, the microdata, and so forth, to validate our approach. When it comes to processing the nighttime light data, basically the monthly composites represent the ensemble of multiple pictures per night expressing the radiance, where cloudy observations are discarded and the images are averaged over each month. However, this data is not good to use already, as it is characterized by noisiness of calibration. There is external influence of non-electric light sources and also seasonality in the values recorded. So what we do is first to identify some noise floor to mask the noisiness and carry out some sensitivity analysis. And then we take the monthly composites for each year and we produce a median yearly value based on the median per pixel value of all the months of the year. Also, there is a challenge as noisiness over unpopulated areas, which is our reference for the noise. So we take areas without population and we measure there what is the level of radiance detected, and we don't expect electrical light there. So we take that as an area where we observe only noise. And then we try to minimize that noise to obtain a clean data from the noise. And also we have to carry out an intercalibration, because if I'm sure some of you have worked with the VIRS DMB data before, and then maybe you notice, maybe we can discuss this in discussion, that after 2017, the data becomes significantly more noisy. So we carry out, as you can see in the figure, intercalibration to make the two data sets comparable across time. Then we assume that where durably lit populated pixels are found, there is access to electricity. Instead, where unlit but populated pixels are found, there is no access or weak or undetected access to electricity by our approach. And based on this, we can calculate population counts, province level, electrification level, and aggregate national level, and then compare over time, taking into account the changing in light coverage and also in population data as a result of demographic change and so forth. We don't only do this binary in terms of light, no light, but we also study separately in urban and rural areas the distribution of light over the quintiles to create some categories of light, let's say, of light intensity for urban and rural areas that can give you an idea of how intense is light in a given area. It's not only a matter of light, no light, but also of how much light and therefore radiance. So we study the quintile distribution in urban and rural areas of light to identify some critical values. And then what we do, we take the official statistics and compare it against our statistics. And we do it on the left-hand side for country level, on the right-hand side for province level of a number of countries, so subnationally. And as you can see, generally, we find a very good consistency of our estimates with the official statistics. But at the same time, we find in some areas that the error grows. In some countries, the error is not little. So in general, the performance is really good, but there are some outliers. And then one can ask, what is the source of this error? If it's a matter of reliability of the official data, if it's an issue of the satellite-based estimation, and it's hard to disentangle the two without ground truth data. But we will discuss this a bit later, also the limitations. The same thing is done for the different categories of light. So as I was showing you before, we classified the light categories with some critical values, and we assigned the population living, let's say, under or above a certain light threshold, and we classify this into different tiers, and we do for a number of countries where we have georeferenced information on electricity consumption. So not only access, no access, but something beyond. So non-binary. We compare our estimates of the different categories of light with some categories of consumption as reported by the World Bank multi-tier framework. We do this for these three countries, Malawi, Nigeria, and Uganda, where we have recent microdata. And although with some bias, we find some good consistency in how light intensity can be a proxy for also electricity consumption at the local level, although the robustness is mixed, as you can see, between urban and rural areas and depending on country. Before showing you some analytical results, some important methodological limitations of which we are really much aware. First, that light detected at night is only a proxy of electricity use. It's not the actual physical measurement of electricity or energy. And secondly, that the satellite overpass is around 1 a.m. the night. So it's definitely off the electricity consumption peak. And this is very important, in particular in rural areas where at the night there might be very, very low consumption of electricity. And so also in sparse settlements, as I was saying, in rural areas far away, it's often very challenging to distinguish between noise and anthropogenic light, and more investigation is required in the sense. This might be the origin of some of the bias that we find when validating against the official statistics. And therefore, we argue that there is need for more granular, more abundant field data to calibrate more precisely the statistical model that can improve the reliability of this estimation. We then, based on this approach, did some analysis. For instance, here you can see we tracked the recent progress at the country level, but from this bottom-up approach, so from very fine resolution in terms of the progress in electrification, and we can show the heterogeneity across countries over time. This is 2014-2019, comparing also on the y-axis with the population growth. And we can do this separately then for urban areas and rural areas, which can give you a better sense of the underlying dynamics within countries. And then we can evidence some hotspots. For instance, here we show which are the areas in the African continent where population without access to electricity is growing fast. So areas where there is a stronger demographic growth in areas which we find to not have access to electricity. And this gives an idea of the growing vulnerability hotspots also. And then also showing you with this criterion of classifying into tiers of access based on the light intensity, we can produce a picture at the country level of how the quality of access is distributed. Of course, this again is a proxy, but it can show you that it's not only a matter of the electrification level in terms of share of people with access to electricity, but also in terms of the quality, the proxied quality of electricity. And you can see a difference, for instance, between rural and urban areas. And also when comparing between countries, you can see significant heterogeneity The output data set is then conveyed in netcdf4 files, a file with the number of people without access to electricity over time, a file with the tiers of consumption in each pixel, and you can find published data descriptor article, an analysis article, and the open data on Mendeley, and on GitHub also the code to replicate the whole analysis or change some assumptions or focus on a specific area and so on. And also we have been engaging to construct an interface where you can play with the data, and it's accessible under the link below, and it can be checked. Of course, there are limitations, as I was saying, in terms of this is a proxy, this is not field data, but it helps to have a more readily updated picture of the situation. Yeah, this is everything, and I'm happy to answer questions.
Thank you very much, Giacomo. We have one question from Hugh. He has asked, did you mention whether atmospheric correction was done or necessary?
I believe that we relied on the VIRS DNB nighttime lights stray light corrected. So we relied on the stray light corrected product. I don't know if this addresses the question.
Yeah, I think so. Yeah, so you're saying the data set you have was already corrected for atmospheric disturbances?
Yeah, I believe yes. I mean, I believe the VIRS DNB product comes already with some degree of correction and calibration, which happens directly on board on the SWAMI MPP satellite, if I'm not wrong. But of course, as I was saying before, there is still some degree of noise before data can be actually used for our purpose. So there is a last layer of noise correction.
All right. Perfect. Thank you very much for joining us, Giacomo. It was great to have you. I'm just trying to see if there's any more questions. I don't think so. Sorry, I was just trying to see if it was comments or questions. But thank you very much for joining us. We're now going to take a short break. We're just 20-minute break, and at 2 p.m. GMT, we will have Christopher Kyba, who will be giving a very interesting presentation, I'm sure. So yeah, I'll see you in 20 minutes. Hello, everyone. I hope you all had a good break. Welcome to anyone who's just joined us. And in case anyone has just joined us, again, during each presentation, feel free to ask any questions either in the Q&A box or the chat box, or alternatively, you can raise your hand and we'll get you in at the end of the presentation to ask your question verbally. We're now joined by Christopher Kyba from the German Research Center for Geoscience. I hope I got that right, Christopher. And thank you very much for joining us, and take it away.
Great, thank you very much. Can you hear and see my screen? Can you hear me? Just confirm, please.
Yep, we're good.
Great, okay. Yeah, so most of the talks today are about remote sensing using nightlights, and I'm going to actually take us down to earth and think a little bit about those lights themselves and how they affect any kind of retrievals that we do using nightlights. So the basic question from my talk is, when we look at an image like this of Europe at night, where does this light come from? And what kind of lights does it come from? How much is from windows? How much is from cars? How much is from streetlights? And if we zoom in at a particular city and look at, say, Berlin, and see in the center of the city that we have a radiance of, in the day-night band, of 100 nanowatts per centimeter squared per steradian, what does that mean? How many lights are there? So that's a question that interests me, because one of my research interests is trying to remotely sense energy consumption for outdoor lighting, and in particular, the change in energy consumption for outdoor lighting over time. So one of the first things you can do when you're looking at this is to look at the change in light. As the last speaker said, light is not the same as electricity, but it's a start. So we did this a couple of years ago. We looked at the change in day-night band radiance over a 4-year period in every country in the world. So all the countries here, colored pink or red, are growing at a rate of more than 1% per year in the day-night band data. Several of you know that the day-night band has spectral issues. So we see, for example, China and USA look like they're steady. If we were to use a band that was similar to human vision, they would almost certainly be becoming brighter, because the day-night band is missing part of the blue information. So we know that the world is getting brighter, but it's difficult to understand because we don't know what kinds of new lights this is, right? Is this increasing how bright streetlights are, or are we having more streetlights spreading, or is it some other kind of light entirely? So before we can address that question, we have to address the simpler question of what makes up the light to begin with. So when you fly over a city at night, or when you look at the astronaut photographs from space, you get the impression, looking at them, that it's mainly streetlights that's the issue, right? So this is Calgary, Alberta, photographed by the International Space Station. And I love this photo because, or this pair of photos, because they're two of the highest resolution photos ever taken from the International Space Station. And you can see that there are some areas, I hope you can see my mouse, where the city between these 3 years in which the pictures were taken changed from orange to white. And that's because the high pressure sodium lamps were replaced by white LEDs. So I'm going to zoom into a little region down here, and you can see this a little bit better. You can see that we can see each of the individual little streetlights there, which is really amazing. And you see that this whole neighborhood changed from orange to white. So when you look at that, you would say, wow, okay, basically all of the light is streetlights. And this is a thought that has really dominated a lot of activism around light pollution, for example, that street and area lighting is the only lighting that there is. But if we look at another region here, just north of the area that got colored with the LED, changed to LEDs, we see some very, very bright areas, and these may be saturating the camera on the ISS. So it's very difficult for our human visual system looking down at a city at night to really properly integrate all of the light and assign it to the correct categories. And so when researchers have tried to figure out how much light belongs to street light compared to other types of light, for example, they've generally come up with numbers between about 1/3 of the light being streetlights up to about 1/2 of the light being streetlights. So actually most of the light, according at least to the few studies that have been done, is coming from other sources and not from street lighting. So why is it that we need to worry about this? Well, it comes down to understanding what radiance we get in space when we look at different types of light sources. So I want to show you a few examples of this. So here's sort of the simplest case. We have a really well-designed street light. It's only shining downward. And so the only thing we see from space is the Lambertian reflection from the road surface. And we're going to pretend for a minute that there's no buildings around. In that case, it's relatively easy to understand. It's just like daytime. If you look at an intensity diagram, the intensity of light is highest going straight upwards and is lowest going towards the horizon. And when a satellite looks from nadir, the ground pixel is smaller. And when it looks from the side, the pixel becomes larger. And because of that, the radiance observed stays exactly the same, because these two things cancel out perfectly. So that's relatively simple. But what if we have a different kind of a light source? What if we have like a globe lamp where it's glowing in all directions? And again, this is just pretend the building is not there. And let's also pretend for the moment that the ground itself was completely black, in this case with the point source. So if we look at the intensity diagram for the point source, of course, it shines light in all directions equally. But what that means is that if you have a line of like a street lined with these little globe lights, and you look with a satellite from Nadir, you'll see a smaller radiance than when you look from more at an angled view. The radiance will become larger as you go to an angled view. And this comes back a little bit. The last talk had a question about applying atmospheric corrections. Atmospheric corrections at nighttime are much harder than at daytime because there's way larger contrast in the images. And we don't know the emission function of the sources. In daytime, with the sun, it's a very simple source above the atmosphere. And if you're looking, for example, in infrared emissions, you know, it's relatively easy because things aren't that different the way they are at nighttime in terms of the directions that they radiate and the intensities. So then there's another source of light, which is horizontal emitters. So these could be things like billboards or light shining through windows or illuminated facades. And those are now sort of more like the Lambertian reflection again, but now completely tipped on its side. And we saw really nice from Xi Li, these pictures where if you're looking from the wrong side, you can't see the emission at all. If you look exactly from Nadir, at least for a window, you cannot see any light at all coming from the window. And then as you start to increase the Nadir angle and look from the side, these sources will become brighter and brighter. So if we don't know what types of lights are making up our imagery, then our remote sensing retrievals, for example, in the last talk, trying to understand electrification or trying to understand wealth, you're going to run into problems because you may be looking at different types of lights inside of cities compared to the countryside or standalone buildings. So that's where some nonlinearities could crop in. So we wanted to address this very simple question. Okay, how much of the light comes from street lights and how much comes from other lights? Just these two big broad categories. So we did a really nice experiment in collaboration with the city of Tucson in Arizona in the United States. Now, Tucson is interesting because a couple of years back, they renovated or they replaced all of their street lights from hypersodium to LED, and they really dimmed things a lot. The other thing that they did is they introduced a dimming so that from before midnight, when they normally have the light set to 90% of maximum brightness, after midnight, they switched to only 60%. So when the day-night band passes over, the Tucson streetlights are actually quite a bit dimmer than most streetlights in the United States would be, and we should keep that in mind for what follows. So this great photograph taken by my colleague John Barentine, you can look at the building back here and see that it's staying exactly the same in the transition between before midnight and after, whereas the street is becoming quite a bit dimmer. So the other great thing is that the city agreed actually to dim the lights all the way down to 30% of their maximum, and 14,000 out of nearly 20,000 streetlights from the city were involved in the test. So that was really great. And when we look at the city from space using the day-night band on two different nights, we can actually see just in the image by itself that something is going on. So if you look over in the right-hand side, in the suburban areas, you can see that's dim, here's bright. There's dim, here's bright. And if you look up at other regions sort of outside the city, these surrounding areas, they stay relatively the same on the two nights. So how do we analyze this data, right? We don't just look at the picture. If you imagine that a city had only streetlights and had no other lighting at all, then you would have perfect proportionality between the light emission of the streetlights and the brightness of the city seen from space. So if the city doubled the brightness of the streetlights, then it would also double how bright the city was. This proportionality breaks down when you add other types of lights, but the slope and the linearity stay exactly the same. So what happens is basically this whole curve just slides up, and you add in this these other lights that have nothing to do with what the city is doing with its street lights. So now that you understand this graph, I can go to the result and show you that. And you see that the slope is much flatter than what I showed in the example diagram. And that's because the total emission from the city of Tucson streetlights is really quite small. So on a normal night when they're dimmed to 60%, the streetlights only make up about 13% of the total light emission from Tucson. And if the city was not to dim their lights, it would still only be about 18%. That's this high point over here. If you look inside the paper, you'll see that the situation is a little different in the city center and the outskirts. You know, we expect that in the city center, there's a lot more advertising lighting. In the outskirts, streetlights become more important. So I'll let you go and see the paper to see that. But I do want to show you some results from some German villages where we did a similar experiment. Now, in this case, we're not using LEDs. These are high pressure sodium lights that are being dimmed. So we can't use streetlight power anymore, but we have the relative luminance. So it's the same idea. So this is a bright night, and then down here are the dimmed lights. Now, in the dimmed condition, we see that these villages are only, again, about 30% to 40% of the light is coming from the street lighting. Now, if they were not to dim, of course, the street lighting would make a far, far higher proportion of the total light emission from these villages. And this brings me to a point I wanted to make regarding the last talk, that, you know, in the ideal case, many places should not be illuminated at nighttime, right? Villages may not need to be illuminated or not illuminated brightly. And so it would be dangerous to expect that you must be illuminated to be considered developed. And what we actually see is that many regions in Germany, for example, in small villages, are unlit at nighttime in the daylight band, because they are using an environmentally conscientious lighting strategy. So that's the end of the Tucson results. I just wanted to make a teaser basically for a new project we have called Nachtliche Bühne. So this is a German name, so I need to explain it. And before I can explain the name, I have to explain where I come from. So I work at a Helmholtz Institute. The Helmholtz Association is the largest German research group in Germany, basically. And it is the Helmholtz centers are the ones that sort of do the really big science in Germany. So for example, the German Space Agency, DLR, is a Helmholtz center. And the Alfred Wegener Institute, who operates Germany's research vessels like the Polarstern, they're also Helmholtz, they're a Helmholtz center. So Bühne stands for the Citizen Helmholtz Network for Research in, and then in our case, nighttime lights. So this is part of an experiment by Helmholtz to try and see how could citizen science plug into this sort of large research organization that Helmholtz runs. It's a play on words. Bühne means stage. So we can say that all the world's a stage. And in this project, what we're going to do is count the stage lights. So the idea is we want to have citizen scientists go along streets, and we assign them from one street corner to the next. They'll go there and then click the plus button to start doing a transect. And then they come to a light and they categorize it. You know, is this a street light? Is it a parking lot light? Is it floodlight? Is it some kind of a sign, video screen? And then after they've done that, they can give us a little bit more information. So for example, if it's a street light, is this one of these globe style lights like these ones in the picture here, shining in all directions? Or does it have some kind of a shield so that what the satellite is going to see is only reflected light? And in the case of signs, of course, we need to have some idea about how large they are. So we do that using human proportions. And all of this is being co-designed, co-developed together with a team of citizen scientists. So we are person power limited on the project. And if you are interested in this ground truth data that we're going to be developing, please get in contact with me. I'd be happy to have some other people to help me analyze it. So we plan to compare to the day-night band and also Luojiao 1, and also potentially with some aerial imagery we'll be taking over the city of Cologne later this year. So looking forward to your thoughts regarding the presentation and lights on the ground.
Awesome, thank you very much. Just waiting on some questions coming in, but I actually had a question, if that's all right. And I was just thinking with regards to like you mentioned, like nadir pointing can, you know, influence things compared to other types of pointing. So is for different applications, would different pointing angles from the satellite be preferable, or is the main thing just that you have consistency?
Yeah, it depends on what kind of a question you want to answer. From the perspective of sky brightness and light pollution, which is one area that I'm interested in, you probably would like to measure many different angles and probably weight them according to the solid angle of emission. For studies like GDP and population, I'm much less sure about what you should do there. What we see is that there's close to proportionality between population inside of a day-night band cell using the Earth Observation Group's standard analysis and the total amount of light. So it seems that what they're doing of just taking all of the observations and combining them is working relatively well already for such things. The Earth Observation Group, however, is planning on doing a correction to make everything look like nadir. And this will likely have the effect of making the city centers suddenly become much brighter than they currently are, because when you have these street canyons, you often get light blocked in many of the directions, but to zenith or looking down at nadir, they appear brighter. So if you work on with such data, I would be really careful about thinking which of these products is necessarily better for you in terms of remote sensing, population, GDP, things like that.
All right, perfect, thank you. And we've got another one from Giacomo, who did the last presentation. He has asked, do you have an idea of what is the role of window lights coming out of windows?
Yeah, what we know from sky brightness measurements, and actually Shi Li showed this also in his presentation, is that most places become darker throughout the night. The darkening is fastest before midnight and slows down after midnight. So we also see a color shift, at least in Berlin, in the study that we did. The light becomes more red as you go later at night. So this could be due to reduced amounts of light coming through windows and from car headlights. It could also be, for example, advertisements shutting off. And I think that in different places, these have different effects. But what I expect is that in the early evening for sky brightness, light leaking from windows is much more important than we have thought in the past. For remote sensing, or sorry, not remote sensing, but for observing lights from space, the windows are hard to see from nadir and become brighter from the side. And so I'm not really sure how much they matter, and that's part of what we're trying to understand.
All right, perfect. One from Jan Peter Muller, who's asked, Miguel Roman, who led the black marble development, has calculated a surface BRDF product for day-night band available from SNPP. Have you looked at these parameters? They are far from Lambertian.
Yeah, so I haven't looked so much into black marble, but I think that the project is dangerous because it's not only the BRDF that matters, it is the emission function itself. And if you try to measure this from space and correct it from space, there's a little bit of circularity there. So I think that this is an important project, and I think going forward, it's going to make the products better. But if I was going to be trying to do remote sensing on the basis of using night lights, I would be really careful about using BRDF corrected emission for now. Maybe it will turn out to be better, and that would be great, but just be careful, I would suggest.
Okay, and one more question I thought of as well is, I may be wrong in this, but as far as I know, that most Earth observations from space at night don't have much color in them. So is that something that is missing? It's kind of limiting studies related to like the color of light emissions at night?
Yeah, you can see some big effects, particularly with the shift from older high pressure sodium to white LED.
Yeah.
So yeah, so multispectral observations in the future are really important.
Great. Great. Awesome. Thank you very much for joining us. It was great to have you.
Thank you.
Next up, I think is Jan Peter Muller from University College London, and I think he is here now. I think. And yeah, you're muted, Jan, so you just need to unmute.
Yes, good afternoon, good evening, or good morning, depending upon which time zone you're in. So I'm going to give a little bit of a review because I've been working in this area for more than 30 years and talk about the nighttime light imagery. We've already discussed many of these topics before, but I hope to offer a new insight and perspective, and in particular concerning the 50 years that we now have pretty close to of nighttime imaging from the DMSP, about a project that I've been working with Chris Alvidge, formerly of the NOAA NIEC, on the digitization of analog film over a 20-year time period, and then talk about some of the aspects, particularly to do with the spectral aspects of what is being missed with the day-night band, then show some work that has been published on carbon dioxide emission and economic development, and finally land up quoting Christopher's paper about opportunities and challenges. So the first thing to say is that what does it actually represent, these nighttime lights? If you look at the land surface temperature field of this area around Chicago and the Great Lakes in North America, what dominates this area, aside from the city of Chicago, are physical geographical features like the rivers, what you cannot really see on most of the cities. But the second you actually switch your view onto the DMSP composite radiance, then obviously you can see the individual urban developments. So there is no direct relationship between the temperature patterns apart from when you have urban heat island effects, and certainly in other areas of this thermal infrared image temperature record, you have no relationship at all to the urban scenes. So lighting accounts for around 20% of the total electrical energy consumption, which is directly itself linked to carbon dioxide emission, according to reports from 2015. And the per capita consumption of light is around 0.7% of gross domestic product. Now, as we've already seen from a number of previous talks, the lighting has changed dramatically across Europe and North America with a shift to these LED lights from fluorescent and high pressure sodium. And I'll come back to that a little later on. Unfortunately, something that hasn't been mentioned so far is there is also a side effect of light intensity increasing, particularly in the blue. Now, nighttime light on several different publications has been linked both to sleep deprivation in urban areas and has documented impacts on human health, particularly concerned with autoimmune responses such as cancer, as well as natural impacts on natural flora and fauna. Now, the DMSP radiance calibrated imagery, the first official Block 5D system flew in 1972. I managed to get hold of some images from 1971, but I can't find anything from 1960s. And the optical line scanner had a particular kind of scanning geometry in order to obtain these nighttime imagery to try and maintain a fixed spatial resolution across the field of view, which has been carried on with the day-night band. Now, the initial nighttime light data analysis was according to the frequency of occurrence over the compositing time period as a percentage of the whole time period. And Radian's calibrated data only really became available in the early part of 1996 and for limited areas again in 2000. Now, these annual digital composites, which have been used by a couple of different authors, presenters earlier, and the variable gain control is used to acquire the images, with high gain being used to amplify the signal from faint light sources which saturate data from big cities, compositing from two different variable gains. Now, this shows the first nighttime light image I've yet found and that Chris has found, which shows the UK down the left-hand area, and also shows the Edinburgh-Glasgow region, and you can see you get lots and lots of saturation. There's also a small portion of an aurora. Now, these DMSP nighttime images were really only acquired for the purposes of looking at nighttime lights when there's a less than a quarter of a moon, so they're not acquired for a large fraction of the time. And the kind of light sources, and I'll come back to this in a moment, is on the order of nanowatts per square meter per steradian per micron. Now, 11 million of these film strips, and shown on the right-hand side is a rather wonderful example of the whole of North America being cloud-free, and you're seeing a magnificent aurora. There are about 11 million film strips which were selected out of about 42 million, which are lodged in the Denver Federal Record Center, and which were going to be destroyed, but fortunately we've managed to rescue them for another 50 years. Now, the DMSP spacecraft, the other thing that needs to be borne in mind is that they have different nominal local times of the node, equator crossing node, which vary substantially from one F series DMSP Block 5D to another. And therefore, compositing data which come from different DMSP satellites can cause all sorts of problems when you're actually trying to use them in a quantitative fashion. Now, shown on the left is a composite, the first one that's produced by Woody Sullivan III, who I believe is still at the University of Washington, at least he was 3 years ago when I last had some email exchange. And on the right is one of the first second generation nighttime light using, in this particular case, digital data. The first one was used from analog data. So all those digitized film products are now available at my lab, and as a courtesy from Chris Alvidge and Kim Bowell. So looking now at a time sequence, here shown is an annual time sequence from each individual DMSP F satellite, and you can see that one of the most obvious things is the South Atlantic anomaly, which as no one has mentioned so far, which rather dominates this region off the coast of Argentina and Brazil. And you can also see that you do have, in some cases, even though you try and suppress it, aurora, and you also have, even with a composite taken over a year, you still get some regions which have persistent cloudiness, where the cloudiness is not properly removed. So given the fact that you have this level of variability, and even though there are these stable light sources, it's still quite challenging to be able to use this individual data without doing some filtering. Now, we've already heard about the fact that nighttime lights can be used as a political indicator. There's a rather excellent example in Korea, as well as the squid fishing offshore. But there are quite obvious economic and political components which I want to explore in a moment. The first one relates using an aggregation at the country scale. This was published in Ambio in 2000 of the nighttime light frequency in that particular case, looking at the total lit area as a percentage of each country. And apart from a few countries that didn't seem to quite report the true situation that is shown as outliers here. This did manage to obtain global relationships at the country level between GDP and carbon dioxide emissions, which was then applied to actually produce a map. The map at the top is the map that's produced solely from DMSP nighttime lights from the time periods I mentioned earlier with the radius calibrated data. And the map at the bottom is produced from the carbon dioxide inventory. I can't remember, I know it must be Archive Center in Tennessee. And in fact, there's very, very good correlation between the two, which is described further in that paper. Now, going back to an earlier point, when we started looking at DMSP data, we were rather surprised when we had NUTS level 3, which is a rather obscure EU Eurostat's measure of population decided on a country by country basis, and it's different size for each country. But when we actually look at this NUTS level data, and we look at the former Federal Republic and the former German so-called Democratic Republic, East Germany, we can see very substantial differences between these two. And this is also possible to use this data in a country where we have very disaggregated lighting, like the Netherlands, to actually look at different economic sectors between agriculture, industry, and services, and therefore be able to determine what is the strength of each of those. That would be very interesting to do now, obviously, with the City of London and various other financial areas which are no longer switching on their lights in the evening. Now, using those relationships for each individual country, and we did this also for the United States, we could produce a gross regional product map, which had an accuracy of greater than 80%, and which very clearly shows the dominant impact of urban centers like Paris, Barcelona, Madrid, Milano, Torino, and various other Italian cities, and also the Ruhrgebiet in Germany and various other cities in the Benelux countries. Now, coming back to VIRS and what does street light represent, here you can see a spectral responsivity function in the gray of the DN day-night band. And in particular, I'd like to highlight the LED street lights, this green area, which shows this very strong peak in the blue, which, as I said, is related to various disturbing health impacts. And you can also see how this peaks around the green to red, and how this is very different to fluorescent lighting, and also very different to the high pressure sodium that we saw earlier. Now, the VIRS instrument was first flown, of course, on the Suomi NOAA Polar platform, which was launched at the end of 2011, and including the visible infrared radiometer. And that, of course, is an update to the DMSP operational line scan system, having had quite a lot of input from the designers of the previous system. And SNEP began systematic production in January of 2012, and you can obtain all of these. And it appears that Black Marble products, when I looked yesterday and could find this information relatively quickly, only since 2017. And now, of course, we have NOAA 20, and there are also NOAA products which appear to be being produced in parallel. So I'd like to talk for a moment about the actual range. Now, this particular camera uses a technique called HDR, which allows you to take multiple images at different gain states. And you want to be able to cover the entire range, going all the way from the aurora down here at nanowatts, all the way up to sunlit clouds and land and sea ice, which are in the milliwatt regions. So we've done an analysis, and the paper is currently in review, and looked at air glow, which is down at the 5 nanowatt level, all the way down up to sunlit clouds over snow and ice. HDR operates very well apart from extremely dynamic phenomena such as aurora, because you get very strong artifacts, and lightning being another case in point. Now, when we actually come to look at the full-scale resolution, you can see here one of the most interesting aspects is that the VIRS shows individual villages near Delhi in India, which are all merged together and smeared out in the DMSP product. And we can also use the change in lightning, which was also shown by an earlier author, here for looking at areas where you have pink or mauve, you have reduction, and areas in cyan where you have increase. And one of the things that you can see very obviously here, and the first presenter showed an example of this region here, is the substantial reduction as a direct result of the Civil War. But one point that hasn't really come out so far is the fact that the nighttime light data, in particular, the nighttime light data of a country like China, is very different depending upon whether you use the DMSP, not just because of a 2.7 kilometer resolution, but also because of the much better MTF that you have with the VIRS day-night band. And just to point out on the way is that there is spectral information available. M8, M7, M8 and M10 bands all show nighttime light features. So, but of course, those are not necessarily the ones that you would choose in order to look at different sources of night. But just to make this point, that if you do try to continue time series between DMSP and VIRS, you will run into problems for these reasons. Now, looking at what, and this of course is one of the reasons why we're attending this workshop today, it's partly to hear from our colleagues at Alba Orbital about what they have planned, is we can see that as a function of spatial resolution and time, that the DMSP has given us essentially the core data set for the order of more than 40 years. And we can see that the Argentinian SAC-C and also the ISS astronauts that I'll discuss in a bit more detail in a second. You can also see where the VIRS day-night band sits. And now we have a series of instruments, both from Aerospace Corporation in Los Angeles through to systems developed at LISMARS in Wuhan. We can see that we're having increasing spatial resolution in order to be able to look at much more of these detail aspects, which is one of the things we desperately need. Now, if we take a look at, for example, Sentinel-2, this is a seasonal composite produced at 20 meters. We can see that urban areas are almost invisible. It's a grey mush, as I call it. We can see certain areas in London, like we can see the reservoirs, which are close to Heathrow Airport, which these days, of course, have most of their lights switched off. And we can also see some of the development of the City of London in this region here. But as soon as we look at the International Space Station at around a resolution of 50 meters, and one of the problems that I found is looking at the ISS, almost all of them either don't have proper forward motion compensation or are blurred because of atmospheric effects. So the quality of a great proportion of that ISS archive is, I think, fairly limited. But here you can see, as a piece of history, we had a small portion of our orbital ringway, or beltway, as it's called in the US, which was lit. And then 10 years later, almost the whole of it is lit. There's just a few small sections left where it's not lit. And this is the best resolution image, which I estimate to be around 30 meters ground separation distance. But again, it's still pretty blurred. So we need something which is much more rock solid. And this brings us to the fact that one of the advantages, however, of having astronauts, and this is from Chris's work, is that the astronaut can keep clicking away and looking at that particular city for quite a few minutes as the ISS passes overhead, so you can actually see the changes. And so it would be very nice if we had some kind of monitoring global system, and I don't think that having something at L2 to balance the Discover Epic at L1 would be appropriate. You wouldn't get the resolution. But if you had a constellation, perhaps a CubeSat, that would actually snapping away every 5 minutes, you would be able to look at the temporal variability. So in conclusion, and taking it directly from Chris, we have a variety, and I've only clearly indicated a few of these, in atmospheric sciences, in ecology, in energy, in epidemiology, which we really didn't get into, and in light pollution. But I think that obviously light pollution and socioeconomics seem to me to be two of the most fruitful areas, but also in the case of looking at CO2 emissions and seeing how well countries are actually complying with the Paris Accords. Thank you.
All right, thank you very much, Jan. That was very, very interesting. We've got a few questions for you. The first one asks, are there any studies completed that you know of that show how nighttime lights affect the photosynthesis project and life of plants in general? If so, does that mean that the amount of CO2 is increasing or decreasing? I think going back to your kind of comparisons with like CO2 output.
Yes, very good question. I'm not aware of any published studies, but that doesn't necessarily mean that there aren't any. It seems to be a fairly obvious thing to actually look at. And when we look at a country, for example, like the Netherlands, which do use 24/7 lighting in their greenhouses, either from natural lights, or if the natural lights aren't strong enough, they switch them on automatically. There, of course, the plants themselves are being grown, and that's the reason why in Europe, at least, we can get tomatoes all the year round, even though we shouldn't be able to otherwise. So at one level, the plants that we actually use for food are probably not badly challenged, but perhaps natural fauna maybe, and in particular, animals and birds are definitely affected, and there are studies that support that.
Great. Another one asks, do you know how you would convert the radiance to an RGB image? And Hughes also said, I noticed all of the talks are for large countries. What about the use for small island states?
But well, at the moment, given the fact we only have the day-night band, and until your satellite launches and other ones which have Bayer color filters or whatever they're being used for red, green, and blue, we don't really have that kind of information. In the case of VERS, I have seen published evidence to show that the three bands that I mentioned, M7, M8, and M10, do actually show nighttime lights. But I have pursued the lead author, Chris Elbridge, to tell me whether or not he's done any further work on that, and I'm not sure that he has. Perhaps because I see Zhu-Song Wang is a member of the audience here, he might be able to comment about if there's any work going on at Goddard and Maryland on that topic.
All right, great stuff. There's also Espoir had raised their hand, so we'll see if we can get a verbal question for you. Espoir, can you unmute? Yep. Hello, Espoir. I don't think we can hear you. Sorry about that. I think that's all the questions we've got for you, I think. But yeah, thanks very much for joining us. It was really great to have you along. Okay, next up we'll have Alejandro from the University of Exeter. Hi, Alejandro.
Hello.
Hello.
No, I'm going to share my screen, and also I'm going to share with you on the chat a link to the presentation, so you don't need to struggle copying the articles and that. Maybe I will do it after the presentation, so we don't get delayed. Please, I get not on time, let me know, okay? I'm very bad on this. So, tell me when I start, okay?
Yeah. Everything is good, so you can start anytime.
Okay. Good morning. I'm Alejandro Sanchez de Miguel. I'm currently working at the University of Exeter, but many of my colleagues are either in the Complutense University, where I made my PhD, the second of Seabrook, and obviously some people that collaborate with us from NASA and the European Space Agency. And this is work that I hope you will be able to see very soon, as the paper is under review. The first thing, everybody knows this image. The only problem of this image is that it's fake. Yeah, these colors are not real, and the real image here, I don't need to explain it that much, is this one, no? And why this is important? Why this image and not the other one is the real one? Well, the problem is that, well, we are trying, and hopefully soon we'll be able to release a real color map of Europe using ISS images. But why is so important to have a map of the Earth at night? Well, it's to have an accurate measurement of the light emission. And what's the problem with the color? Well, one of the big problems that we have is the current transition that Chris already mentioned from high pressure sodium lamps to LEDs. For example, in one work that we published 2 years ago, you can see more details in the article. For example, we studied what happened in the city of Milan, this with images of the ISS. And to see it in a different way, if you see those two images, the change is not very clear. Maybe the right one is a bit more lit. But when you have the color information, you have much more information. The change is much more dramatic. And now the intensity change is not so clear. When we see what happened with the beers and inspecting Milan, we see that Milan had a decrease on beers over 50%. That was real or was not? Well, the thing is that if we compare with what our eye should see if we were in Milan before and after, we don't see any change. And the reason is because the municipality of Milan changed the illumination to match the same photopic vision before and after. But the beers don't see that and produce a problem. No? If we consider the photopic intensity, yeah, but if we consider the blue light that is linked with many environmental issues or health, there was a 27% of increase on blue light. So it's a problem, no? One of the things is that beers is sensitive to infrared light that humans don't see, that don't produce light pollution, and indeed, many cases it's a kind of noise for us, depending on what is your goal, no, your target. The blue light, in other hands, humans see that blue light, cars produce light pollution, produce environmental impacts, and produce impacts on human health. And in more detail, this is the spectral responses of the BES, DMSP, and SQM. SQM is Square Quality Meter. And we see here the DMSP and the BERS. Here they are the ISS. These are the two areas that we should think about. And we should not care only about the blue peak. Also, we should care about the high-pressure sodium lamps have a heavy emission in the infrared that the other kind of lights don't have. So, for example, when we change from high-pressure sodium lamps to LEDs, even if the photopic part don't change, that would be something like the green area, yeah, something between the green and the red area, the infrared and the blue change dramatically and produce these problems. Well, we presented all this in this paper, where we released many other things, like how you can classify and predict where the spectra of streetlights can be seen, how to produce photopic vision maps with the ISS images, and even create other indicators. But one of the things, for example, is in this paper is only using two channels, but we also did another paper that not so many people know, is using the three colors. No? With the three colors, we get even more accurate information for the human eye. This work, no? The calibration, no? Because this was a work made mainly using relative calibration, no? So now we are presenting the steps that we are preparing for the radiometric calibration of the ISS images using stars to get the absolute calibration. It's true that we have some issues in terms of sometimes the pictures are not taken from the same window, so there is some corrections that probably will need to be fixed later on in making an intercalibration, but we fix many of the issues that the ISS images has. For example, we fix the non-linear regime of the ISS. This is an example of a very wide 24 millimeter image from that you can see in the center Madrid, and on the edge you can see the Netherlands. It's very important that the people try to use the raw images of the ISS and not the JPEG, because the JPEG have first is a loose compression, and then also many times there's areas that are saturated in color and you are losing a lot of information. For example, on these topics that I'm commenting on the LEDs, no? And here you can see how in the bottom part in the JPEG nearly you cannot distinguish any colors, but when the same image is adjusted using the raw, you really can see how there's huge differences between different areas. This is the area of Madrid. But what happened that dealing with the raw image is not that simple. In reality, is 4 images embedded in one. So what we do is we extract all the information in 4 images, green, red, 2 green images and a blue one. Then also we consider how the image is deformed to using geometrical transformation, elementary geometrical transformations to infer where was truly the nadir where the ISS was taking the picture, because the time that the ISS gives to the pictures is not the real time, is the time of the camera, and a small the offset of seconds can mean hundreds of kilometers. No? That's why it's quite difficult to find high resolution images. For example, we can have up to 5 meters per pixel with the ISS, as Chris saw in his presentation. But many times it's difficult to find because they are not in the area that you are trying to find them. We also correct from the flat field or vignetting. This is a correction that honestly anyone using an ISS image should do, no? Because you can see, for example, here how there is a huge difference between using an ISS image that you have your subject in the center of the image or in the edge. We tried to buy all the lenses that are using the ISS to be able to correct all this effect. Here is calibrated, it's not stretched, but so you see more or less the values that we get, the units. And this is geo-corrected. You can see how effectively we can correct the deformation of the image and get a huge area. Obviously, the resolution in the area more close to the nadir is higher than the resolution that we have farther away. We also, as we know the location of the true nadir, we can also calculate what is the angular distance in the image and make an atmospheric correction. Here, this is the already calibrated image of Madrid, well, of the image that I saw you before. But one of the issues, as I said, is the intercalibration, no? Because many times we want to compare with other images taken similar area. We can have issues like the moon, or well, just that the images are taken in different windows and we want to use a common reference. So, for example, what we did here is take the output of our algorithm and make an intercalibration with BIRS. No? In this case, is not very high resolution ISS image because we are using a 24 millimeter image that is very, very wide. But this is the area of Madrid. And for example, you can see how, as this image is taken much earlier in the evening, you can see how the center of Madrid, the financial center, is lit. Although here, for example, the only thing lit in the center is the Santiago Bernabeu football stadium. So with this, we can fix the problem of acquisition. And this is the comparison, no, between the images. This is the density plot that we use to create the intercalibration, no? And the intercalibration fits nearly perfect with a one-to-one line that is the red line. We don't trust these dates, okay? I put it a bit approximately, but this allows us to make intercalibrations between, for a specific city, like can be in this case Barcelona, and see how specific place, like can be the Zona Franca, the port, is changing in color. Also, we have to consider that we have ISS images since 2001. Not many, I have to say. Most of the images that we have are since 2012, but some even we have quite early. And the range of resolution that ISS can produce is from 5 meters, not many images, but in very relevant places, up to 200. No? And many times we have time lapses, so that covers a huge area that we can process. Here is an example, so you can compare BIRS, LIWA, ISS, and daylight. This composite was done by Chris Kyba. And in these ISS images, we can see things that we cannot see other way. No? For example, the difference of color between East and West Germany, the border between Mexico and the US, the color change in the north. And well, this is all. Just one last thing. If you want to get these images calibrated, how you can get them? Well, you can collaborate with our project, citiesatnight.org. You also can hire a spin-off company from the project that more or less many times we can make better deals, but the price usually is 1,000 euros per image. And also you can wait that we make the data release from the mission project. That is where I'm working right now. That will be a lot of images for everybody, but mainly for Europe. And if you have any questions, obviously, also you could hire me. Opportunity opening soon.
Perfect. Thank you, Alejandro. We've got one question so far from Natalia. Natalia asked, how do you transform DN provided by ISS into radiance units? Does Nikon provide any official formula?
No, they don't do it. We do it. Well, you will be able to read all the details in the paper. No, that we are. This is the title of the paper is the same as the presentation, and I hope it will be released very soon. What we did was use the stars to calibrate in an astronomical way the cameras, and then intercalibrate the cameras. What we did is we have a copy of every camera that has been in the ISS and every lens that have in the ISS, and we took all this to the lab. We made intercalibration between all these cameras, and one camera, the D3S, that is the most popular with the 50 millimeter, is what we use images that the astronauts took with the stars to transform it in radiance units, and then intercalibrate with all those. But also we compare with beers, no? Obviously, the comparison cannot be done immediately because the beers and the DMSP and the ISS has a different spectral response. So what we use is photometric synthetic photometry to simulate what the ISS, what the beers image will be, knowing the information that we have from the ISS. So it's not a straightforward process, no? And I hope at some point I will be able to release openly all the code, but currently, well, it's still in development, and even I don't have a job yet for next year. So currently, we are not going to be able to release all, but we'll release some parts of the code, and it will be the paper. That is how we did it, no?
All right, great. And one more from Ken. He asked, how accurate is the ISS position data for each image?
For the images, no, it's awful. Usually the original images can have errors of 500 kilometers or even more, 1,000 kilometers. So you really, I have not talked about the citizen science part of the project, that is locate the images themselves. But yeah, it's huge error, no? Then when we do this process, I cannot tell exactly what is the error that we get with them, but can be maybe 10 kilometers or so. I'm doing it a very broad estimation, no? But around that.
Okay, thank you. And one more from Jan Peter Muller. He has asked, could the day-night band be used to automate geocoding of the ISS images?
I didn't understand you. Can you repeat?
Could the day-night band be used to automate geocoding of the ISS images?
Very good question. Very good question. We are also working on that. is possible for the low resolution images, yeah, but needs training, needs development. Definitely is possible because we are working actually on that, no? And well, part of the some of the funding that I'm requesting is in that direction.
All right, great. I think that is all the questions we have for you. So thank you very much, Alejandro.
A pleasure.
Good to have you. Thank you, and thank you to everyone for all your questions as well. Like, the more questions, you know, the more discussion, the better it is for everyone. Next up, we have Pouya and Hessam from Hatch and the University of Toronto.
Hi, Greg. How are you?
Hello, I'm good. Pouya, how are you?
I'm good. I'm good. So, can you guys see my screen right now?
Yep, we can see your screen. Yep.
Okay. Perfect.
We've added Hessam as well in case he wants to come in.
Yes. Thank you very much. Hessam, as you see here, is a great friend of mine, and he used to do his master's actually at the University of Toronto when we started this project. And then he went on to his PhD, but we carried on this project kind of on the side together. First of all, I just want to say thanks for the amazing workshop and the great lineup of presentations that you guys put together. It's very interesting. It is very as well focused on the nighttime lights. Our presentation is a little bit different, I believe, because we are trying to focus more on an application domain of the nighttime lights. So generally, our angle into this from the beginning was try to create project analytics systems, and that would be for example, mining projects or resource projects, or even infrastructure projects. An industrial partner to our research, who I'm working there right now, Hatch, is a Canadian engineering firm, which was managing a big portfolio of different projects. And it was very important for us to create project analytics outcomes, like a framework that can help us assess the risks of these projects, kind of follow on them, and have a better handle on different aspects of them. And we divided the problem to three main parts, as within designing the intelligent system, to representation, learning, and inference. And within the learning side was where we realized that there could be a potential of capturing remoteness risks based on nighttime satellite imagery, which ended up to a paper that kind of led to my our discussions with Alba Orbital later on. I'm very happy to be here and quickly review what we did and how we try to characterize that. So a little bit on the prevalence of remote project. This is a graph by Pryor, a study that he done in Australia. It shows that from mid-19th centuries to early 21st centuries, the average copper ore grade actually fell from 25% to 2%. That means that as the world is kind of depleting the better and more potent resources, we have to look forward to more perhaps remote resources that we can tap into. And one interesting observation here is that given this decline in the average copper grades, for example, and this is true basically for most of the commodities, the total amount of that we produce around the world of copper is keeping increasing. And that's because actually we are doing that. We are tapping towards more remote, inaccessible resources. And a major part of that is that remote resources, they have to be big enough to kind of pay for the cost of the infrastructure that needs to get there, for the cost of the, like they have to justify the big investments that goes into kind of making them accessible. And with that, there is a whole lot of investments on remote projects around the world, which and a study that was done on the effectiveness of such investments kind of resulted in a very, very poor and metrics comparing to the projects that are less remote. And all of this is perhaps common sense. The remote projects was shown to have suffered from cost overruns, schedule slippage, and operability problems for 30, 29, and 70% more, which is a high difference between these for this specific variable on definition of the project. And the important so the thing is that here what I wanted to say is that within the industry, within the projects industry, the way they categorize this remoteness is quite crude and coarse, in a sense that they divide it to three categorical, they divide it to a categorical variable with like 3 states of non-remote, remote, and semi-remote. And they come up with like very random justification for that. For example, they say if it is closer to 100 kilometers, we call it out to a city, we call it non-remote. If it is more than 300 kilometers, we call it remote. And anything in between, we call it semi-remote. So this kind of led us to think that, yeah, perhaps could be a better way of continuously and automatically categorize these projects. And we looked into nighttime lights quite extensively. We as Hatch, actually, we did a project in Pueblo Viejo in Dominican Republic from 2008, which I'm not sure if you guys can see that Red Cross. The Red Cross has been the site of a very remote mine that kind of went through an intensive expansion from 2008 to 2012. And we saw that not only the location of the mine got lit, but as well some of the cities surrounding that position. And there has been, I'm aware of several other studies that done similar comparisons, which got us to a point to realize, to think of how we can do that remoteness quantification. Now, we were able to find a remoteness index of Australia that was published for 2011. And this is what you can see on the left. It's called ARIA, Accessibility and Remoteness Index of Australia, which kind of divided the whole remoteness range to a continuous variable from 0 to 15. And they actually calculate these by going into like taking census data, and then as well taking commercial data. They define some service centers around the different communities and calculate the relative distance of populations to those centers. And we kind of, when we looked at it, and then we looked at the nighttime lights of Australia, we thought, yeah, there is definitely some version of correlation there. And so I'm gonna quickly, and then we kind of defined the problem as a classic machine learning problem with the predictor variable and the target variable. For the target variable, we chose the ARIA, and for the predictor, we chose the average radius calibrated for 2011. We were lucky, because we had both for 2011, so we could kind of cancel out some of the errors that could have been there because of time differences. And the other aspect of the problem that we dealt with was that although the ARIA was published, was actually built as a continuous variable, what we had was a map of certain different regions, which only could help us to solve this problem as a classification problem, whether we can classify certain points within Australia as any of these regions. However, we did try that, but as well we did try another way, which that we thought that, okay, perhaps we can find the points on the borders of these categories, and then that would allow us to actually solve the problem as the regression problem and get to a continuous gradient of remoteness, which is what we did eventually and end up having actually better useful results. So the other thing that I was going to talk about within our feature engineering is that there is this law of geography that we learned about, which was very interestingly stated, that everything is related to everything, but within the remoteness, the concept of distance is of importance. So how we went about this was that we defined certain classes of features with certain radius of effectiveness around any point. That would be 100, 300, 500, and 1,000. And these, again, we chose them based on the significance within our model. And we masked out the seas and the open waters and tried to calculate the specific features of the intensity and the distribution of the night lights within that radius of effectiveness. So we got our features, we got our target variable, which was the Australian remoteness index, and then we actually built the model, tried to validate the model, and eventually calculated our remoteness index on the validated model for the whole continent of Australia, which ended up to match the area quite well. And this is, as you can see, this is what we call nighttime remoteness index NIRI for 2011 for Australia, putting on the same slide with the ARIA index. Now there is this is a little bit of the kind of performance of our models. We tried different types of let's say machine learning algorithms and different types of sampling methods. Eventually, we chose EARTH, which is a specific let's say implementation of a method called the multiple adaptive regression splines. The method called actually MARS, but since it is copyrighted name, so the code that is developed is called EARTH. So we use EARTH model and SVR, which is support vector machines, at the very end. And we did different types of cross-validation, including a geographical half-split test, which means that we trained our model based on the basically east side of Australia and tested it on the west side of Australia. And with the geographical split test, actually, we got into 0.84 coefficient of determination, which was actually quite surprising for us to see that, yes, although it sounds perhaps intuitive, but we kind of established that the nighttime lights can predict this. And this is very important because these indices, for example, they do one in Canada of these remoteness indices, which is where I am presenting today from. And they're very time consuming to calculate. They're very time consuming to collect because it is based on census and commercial data of services. And usually governments do this perhaps every 1 to 2 years. And our methodology can help, for example, to bridge the gap perhaps between those calculations, instances of calculation of the index, and as well as for projects and stuff for projects that are located on jurisdictions where there is no census data, or they are located in close proximity of two different jurisdictions, which is hard to kind of map stuff like that to come up with the risk method. Now, this is a little bit on the model tuning that we used on with both EARTH and SVM. It shows the basically parameter tunings, which I can talk about it if there was interest later on. And then the next thing that we did was that we thought, okay, we have the 2011 right now for Australia. However, that was the time actually where VIRS-suit results data actually came, was published. I believe it was for the first time, it was in 2018 or something like that. So we thought that, okay, this is pretty good because right now we can use the same model to basically calculate, to get the remoteness indexes for Australia in 2015. Although totally different types of sensors, but our index is quite comparative in nature because we normalize it both. We normalize both our features, and as well we normalize based on the geographic context of the continent, for example, or a country. From 2011, with the first, I forgot the acronym, the first nighttime lights, and 2015 with the VIRS, we saw a big expansion on this northwest part of Australia, which was kind of expected because during that time there was a whole lot of industrial activity going on there, a few very, very large projects going on there, which is actually as well shows an angle that our our index could show that perhaps ARIA or other remoteness indices cannot, because these are perhaps mainly more, this is the mining region of Australia, Pilbara, and they are mainly more industrious in nature of the economic activity there. There is not much established population in cities and all that. And that's why the ARIA, for example, categorizes this as a remote. However, if your angle to this is the risk of remote projects is perhaps less remote than what a census-based index would provide. We did this for North America and Canada. We got the chance to actually check this as well with the Canadian remoteness indices that I mentioned for 2015. And we as well were correlated with Canadian remoteness indices with the correlation factor of 0.84. Now, in terms of how we use it right now, this is the map of, like a NIRI map of Northern Ontario and Quebec. The star points is actually the mining areas, the mining camps within Northern Ontario, the main mining ones, which is actually helping us to define a certain risk factor, overall risk factor of remoteness on any projects that we have on any of the, in our portfolio around any of these camps, basically, as they call it, mining camps. Ring of Fire is the one that is getting developed right now, and it's quite remote. So you can kind of come up with some established quantitative measure of difference between these in terms of remoteness risk. This is the same map for Northern BC and Alberta within Canada. This is Fort McMurray, where there is and Grand Prairie, where there is a whole lot of like oil sands activities going on, and we can see that our index actually quite interestingly collected those. And just to finish my presentation, thank you very much for the chance. We do believe that this was an interesting way of quite with low cost rather quantify remoteness or things to that nature, and we do believe that it has definitely applications in risk management, but as well in resilience planning for remote communities and within policy making, as it is established with the nighttime lights application, I believe, in many of these areas. We proposed our index to go to Statistics Canada as well, and we hope that as more VIRS readings or data come online, we can establish that our index basically annually going forward. With that, I just want to say thank you again, and I'd be very happy to answer any questions, and if there would be need, I can be reached out at my email address.
All right, thank you very much, Pouya. We have one question so far. It's from Christopher Kyba, and he's asked, how did you deal with the aurora light in Canada?
Well, yeah, so that's a good question. So the packages, the data that we use from various and from before that from Earth observation groups, we use the corrected versions of that. We use the packages that was corrected for like a stray rise aurora. For the 2011, we used the radiance calibrated versions, which was adjusted for gain. However, we have an interesting problem here, perhaps on the same note, and that is flare gases. So, for example, we did this for Africa and for South America, and there are situations, locations where there are a whole lot of flare gases there that kind of, you know, tipped our remoteness scale quite low there. I know there is studies on that we can mask our nighttime lights for the flare by Chris Elvidge group, that we can mask our nighttime lights for the flare gas locations and all that. So that is basically our next step in developing this.
Brilliant, thank you. Just checking to see if there's any more questions. I don't think we have any more. So yeah, I think that's us. Thank you very much.
Okay, thank you, Greg. Thank you. You guys are doing it great. This is very informative. I'm very thankful.
I'm glad to hear it. It's good to hear it.
Have a great day.
Good. Okay, now we have at the end of the second session, so we now have another interval, this time for 30 minutes. So we will see you back at 4:10 p.m. GMT, and at 4:10 we have Professor Brian Min from the University of Michigan. So we'll see you again. Thanks. Hello everyone, welcome back. Thanks for staying with us. I'll repeat again, just in case anyone new has joined, that during the presentations, feel free to ask questions for the presenter, either via the Q&A box, the chat box, or you can raise your hand and we can get you in to ask your question verbally. Next up, we have Brian Min from the University of Michigan. Thanks for joining us, Brian. Yeah, take it away.
Well, thank you, everyone. And thank you, Greg, especially for organizing this. Let me start sharing my screen. Boy, it would have been so much more fun to all be together in Scotland, but we're together now, and I'm happy to be presenting and just to connect with a lot of folks in the nighttime lights community. It's very, very exciting. Around the world, over recent years, there has been a dramatic increase in rates of energy access. In India, they have electrified 100,000 villages in the last decade. That means there are some 300 million more people connected to the grid. That's a remarkable accomplishment. Yet at the same time, India continues to suffer from abysmal power quality. In one study, it was reported that Delhi experienced 1,000 power outages in just a single month. Now, those are not problems that are unique to India. Reliability problems remain stubborn in much of the world. Ghana has gone through a period of an extreme power crisis that lasted years. South Africa continues to struggle with power outages. And of course, we're all reading in the news about power outages in Texas, probably one of the last places on earth that expected to have to deal with these issues. Poor reliability is a constraint on economic growth and development. and it has serious implications for the climate. Yet at the same time, despite its importance, we continue to lack reliable data on access and the stability of power supply in much of the world. For much of the last decade, we have been working with the World Bank to develop new methods to exploit the full set of data available in the Nighttime Light series to develop new high-resolution electricity access indicators. Many of you, all of you, in fact, are familiar with these nighttime lights composites. Here is a composite for Kenya. What our team has endeavored to do is to go deeper than the annual composites and move all the way down to the original nightly data. It's from the nightly data that we can then extract time series on variability and light output. That information is then overlaid on top of additional data that is increasingly available. I saw Giacomo Falchetta present earlier today, and so this is a nice follow-on to the work that he and his team have been doing. We also have taken advantage of new high-resolution data on human settlements. This is computer vision-derived data that identifies the location of every building within a country. And if you know the location of built structures, then you can overlay that on top of the Nighttime Lights time series to develop even more refined indicators of access that are highly spatially specific. And so if we zoom into a portion of Kenya, there's a daytime night image, and in pink, you will see identified what the Facebook computer algorithms identify as the location of a building. And so for each of these pixels, we take it as our task to classify each pixel according to the likelihood of access, and it's an estimate of reliability. And so we generate new data that looks something like this, that generates a continuous measure of the likelihood that we believe that that settlement has access to electricity. Now, these access indicators and reliability indicators come from a nightly comparison of nighttime light data. And so this is not using any composite product, but actually going back to the original nightly time series that goes back for years, back to early 2012 and extends to the present. That is then a remarkable historical record of hundreds of nights of data that both tell us what the light signatures look like over electrified areas and what it looks like over areas that are not only not electrified, but have no settlements. It ends up that by incorporating the full portion of data available within a country, we can identify and extract even more useful knowledge. The general principle of our HREA approach is to compare on every single night. So within every night, we look at the imagery, separate out settlement pixels from non-settlement pixels, and then engage in a matching exercise where for every pixel that it has a settlement, we compare the level of light output to a set of matched unpopulated pixels that have the same land cover and are captured on the same night. Now, the advantage of this is that it controls for other factors that we know are important contributors to light emission detected by the FEEM satellite. In particular, lunar illumination and its interaction with land cover. And so I'm in Michigan. If I look out my window, as I did last night, you almost don't need any lights on outside to be able to see around because the moon is, because there's moonlight and because we've had a recent snowfall. And so snowfall areas have high reflectivity, as do certain types of desert and other types of land cover. Controlling for all of that then, each night we're able to derive an estimate of the statistical likelihood that a settlement pixel has higher light output than unpopulated pixels. That then gives us a statistical estimate each night, which we can aggregate across the calendar year. This zoomed in sense of what that output looks like. So here is an area just outside of Nairobi in which, using that full time series across 2017, we can identify not only the areas that appear to have very high and very stable light output across the calendar time series, but and not only areas that have a very low likelihood of having any access to electricity because we never see light output in those regions, but we also identify a large number of settlements that fall into this middle range, which maps on very well to what we are increasingly understanding about energy access around the world, that this is not a binary phenomena, but that homes enjoy different levels of access that are impacted both by reliability and also by low levels of usage. And so we generate this type of data across a large number of countries around the world. Now we can work hard, we have worked hard to ground truth and kind of do our best to test the validity of our estimates. And so here's one comparison in which we compare on top our satellite-derived HREA estimates with some ground-based surveys that were conducted several years ago by a team at Berkeley, in which they went door to door and identified homes that had access and did not have access in a part of Kenya. And in this direct comparison, you can see in panel A, for example, that our estimates identify high likelihood of electricity access right by the water's edge. And that's exactly the same pattern that was detected in the ground-based surveys. Panel B finds a similar type of comparison as well. And so some of the village level and household by household level comparisons have produced some very encouraging results. But we can also compare more globally across the country. If we take all of our statistical estimates and aggregate them up, we can generate estimates of the electrification access rate at the country level. And compare that with what is, for now, the best available data, which is reported in the SE for All reports at the World Bank. And so on the y-axis are our World Bank estimates. On the x-axis are our HREA estimates for this first batch of countries for which we compared 33 countries over 5 years. The correlation is so high that, in fact, just looking at the scatter plot, you wouldn't be sure which data was based on ground truth, which data was estimated. And just to underscore the point, while surveys are laboriously collected, the satellite-based estimates are automated. And in fact, we have the ability to generate more frequent and more regularly updated satellite-based data than is possible by surveys. We are in fact working right now on computing estimates all the way up through 2020. We have launched a pilot of our HREA data, which is now accessible and publicly available. And so I encourage you to visit this website. You can also find the link on my personal web page if you just search for my name. We have now shared HREA data annually across the time frame for which we have VIIRS data for about 25 countries, and we expect to continue to add HREA data from many countries around the world. So I invite you to explore this website. Lastly, let me actually point you to something that may be of even broader interest and excitement to this community. If you have not yet seen the announcements very recently, in fact, just a few weeks ago, in collaboration with the World Bank, we launched the Light Every Night dataset, which is the complete archive of original nightly data collected from the VIIRS day-night band sensor. It also includes every raw nightly image collected from the DMSP-OLS sensors. This is data that NOAA has produced over the decades, and in theory has been open access and in the public domain. But up until this point, it has always been a challenge to gain access to the original nightly images. It's always required some customized data pulls by staff at NOAA. But we're grateful for our collaboration with AWS, which has agreed to publish the data on its open data sets program. And so all of this data is now accessible and available. I'll encourage you all to begin exploring it as well. It is a massive data archive. It's about 250 terabytes, which we believe is the largest single access point that provides access to all of the nighttime lights data. And so with that, thank you very much. And it's a pleasure to be with you today.
All right, thank you very much, Brian. I'm just waiting here just to see if any questions come in. Yeah, I think we've got a couple. Jan Peter Muller has asked, would it be of interest to add the 1971 to 1992 digitized data to the AWS Open Data Platform?
Boy, what a fascinating question. Jan Peter, I am interested to know whether you are indicating that you have access to some of this data. I think that'd be of great, fascinating scientific interest. My understanding is that a lot of this data continues to sit on film, and so I was not aware that any of that data had been digitized in a systematic manner. But as for those of us working in this domain,
he just said that Noah shared 11 terabytes with him and Chris Elvidge, with him before Chris Elvidge left Noah.
Yeah, Jan Peter, I would love to follow up on that. I think that'd be of great interest, and I'm sure, I mean, I can already see others responding positively as well, that this is, in fact, I mean, I've often said, perhaps the most important historical data source we have on human activity that goes back consistently over time. And so, so Jan Peter, I'd love to follow up. In fact, I will make a note to reach out to you if I don't hear from you first.
Perfect. It's good to make things happen, I suppose, out of this. We also, Christopher Kyba has asked, how did you deal with the different positioning of the pixels from night to night?
Yeah, Chris, that's a really good question. And at the level of detail that we're trying to do this work, you're absolutely right that even slight movements of the geolocationing can have a big impact here. I don't know if we have a terrific answer to that. In fact, I mean, some of our effort is premised on this notion that with enough data, some of this movement washes out in the noise. We also do continue to follow on with kind of the standard approach adopted by NOAA, which is to really focus on the center portion of the swath of every suborbital swath where the geolocationing is better, and so to kind of leave aside those at the periphery. The other thing, just on that note too, I think one advantage of moving to the nightly data is that it actually allows you, especially if you're in a framework of where you have some comfort with dealing with noise, of actually incorporating more data into your signal stream. And so many of you know that NOAA has historically been very conservative in preserving only images from the darkest nights with the least lunar illumination, which makes sense kind of if the only thing you care about are the brightest sources of ground-based light. But if we're also interested in these dimly lit areas, then you may want to soften some of the thresholding that goes into the selection mechanism for the composites. And so that's one thing we've done in our approach as well, to incorporate just a little bit more data. In fact, we've realized that, you know, on just allowing a little bit more moonlight in, actually our statistical algorithms can still handle that without a problem, and it increases the raw data that you get to work with.
Great, thank you very much for answering those. I think that's all the questions we have here. So thanks again very much for joining. It was great to meet you. Chris is just saying that's very exciting work. He also asked if you could post the link to the daily data in the chat, sorry, which I'm sure
I will do so. Thanks.
Right, thank you very much. Thanks, Brian. Okay, next up we have Tom from Alba Orbital, who's the CEO of Alba Orbital, and he is going to talk about Alba Orbital's work in the world of nighttime lights and the stuff that we have coming up.
Thanks, Greg. Yeah, and I just want to thank everyone for taking part in this event. We started researching this a couple of years ago, like Greg said, and one thing that kind of seemed apparent to us was that there's a lot of similarities to the Pocket community, which is a small satellite community that we're part of, and we help get people to orbit, and we've done that for a while. But certainly it seems that the NightLights community, is a lot of cool stuff happening, but it's not very well connected. That's in, hopefully a lot of the talks today, people are, all working generally towards the same direction, but it's kind of siloed. So really part of the event was to start and bring people together and work on new use cases of the imagery and just share best practice, basically. There's a lot of papers out there, but it just seemed that people maybe weren't, sharing that knowledge very freely in some sort of like conference style sort of workshop type forum. So that's like why we've done the event. And also we also have some sort of interest in the spacecraft side of things, because we actually build spacecraft. So I'll just give you a kind of overview of who we are, what our background is. Obviously we have things online that people can go check us out, but this will be specific about our imaging satellites, and particularly NightLights, and then where we're going with that. So our vision is basically to, or sort of our belief really, that satellite imagery of night should be commercially available, it should be affordable, it should be high resolution, and it should be dependable enough to build new and existing use cases and potentially business use cases on top of that. It seems to us that that's really something that's missing in the community just now. There's obviously 3 or 4 different sources of data, and each of them have sets of pros and cons, and we think there's a bit of a gap for a dependable, reliable satellite stream that's high res, basically, or relatively high res, I should say, compared to existing options. So yeah, this is us, this is our team. We're about 15 people just now. We're based in Glasgow, Scotland, albeit we're now a US corporation. And we also have a German subsidiary. So we actually technically 3 Alba Orbitals, 1 in North America and 2 in Europe. And all our ops are primarily in the UK. We have Earth stations out in Germany for talking to spacecraft, but essentially that's how we're set up. I founded the company back in 2012. So we're coming up to 9 years old now, which is kind of crazy. Most of my vast majority of my adult life has been building Alba. And I think the thing that's probably the coolest achievement in our history is we managed to bootstrap ourselves to orbit, which basically means that we managed to get a number of satellites to orbit without taking external investment, which is typically seen as like a near impossible challenge for fledgling startups to do. So that's kind of our background. Yeah, so kind of our credentials in terms of satellite building and launch. We've launched 6 satellites to orbit so far. So that is, basically more PocketCube satellites than any other organization in the world at this stage. We have another 9 that have already shipped out to Cape Canaveral for a launch with SpaceX. And that was actually supposed to go up in January, but it's been pushed into a June launch. So when that goes, that'll be 15 that we've launched. And these are primarily ride shares. We aggregate other customers. So they come to us with their satellite they developed. We aggregate it and we launch it. But we also develop our own platforms. So we've flown 2 Unicorn satellites, which I'll talk about in a second. And we essentially do all the technical chain from image capture all the way down to receiving the image and serving it up for folks. And we have lots of customers and stuff. Some big name ones are Stanford and Carnegie Mellon and TU Delft and European Space Agency. I'm not really going to stress the use cases of nightlight data. I mean, I'm probably preaching to the choir, to be honest, on this one. And you guys have probably, I think all the talks so far have done a much better job at explaining the people's interest in nightlight data than I possibly could. But needless to say, we see that there's obviously a lot of applications of nighttime imagery, imaging Earth at night. My talk will be a little bit more just about the space segment and the satellite portion of that, because I don't really feel I can do justice on the application side of things. So, because we have lots of great talks, and I think I'm not going to sort of to follow that one up, but that's sort of where we are. But in general, we see lots of use cases. They've been talked about. And really the thing that's needed, obviously, is like good, reliable EO data and good resolution that's dependable. And that's what we think we can help the community with. So the hardware. So our satellite platform is called Unicorn. Unicorns are pocket cube. Pocket cubes are sub 1 kilogram satellites, and Alba is the world leader in that sort of technology. We've developed a bunch of stuff. Basically, we've developed the full platform. So we've developed the world's largest deployable solar panel for any spacecraft under about 100. Well, yeah, it depends how you classify it, but it's certainly the most powerful spacecraft under 1 kilogram, if not under like 5 kilograms, with our big wing. We have a full pointing system, so an ADCS. So basically, that allows us to point the spacecraft. So no other company or any other organization in the world has been able to make an ADCS as small as we have. So that's something that's pretty unique to us. And we've developed a high-speed S-band downlink. So that allows us to get images down. And we're the first people in the world to do that for pico satellites, essentially. So that's kind of our background. We're a pretty hardcore technology R&D house on that side of things. And really, why am I mentioning this? Well, this is basically going to be our tool to build a constellation of satellites to image the Earth in unique ways. And yeah, that's the background. So as you can see, there's the lens, there's the sun sensor, there's the radios, and these are some of the magnetorquer rods there. And this is the antenna up this bit here, so if you guys can see that. So Unicorn 2A. Unicorn 2A, ironically, is not our first satellite. There's been a Unicorn 1, and there's been a Unicorn 2B and 2C. 2B and 2C have actually launched already and actually re-entered. So it's a little bit out of sequence. So if, just for you guys to know the numbering scheme. So as you can see, this is one of our engineers holding the satellite. So for a sense of scale. We can do 24-meter resolution on that. RGB swathe width is 62 kilometers by 48, and we're flying on a SpaceX flight in June. Essentially, we integrated that in October. It was due to go on a January flight, but like I say, it was pushed back. And that's going to go to a sun-synchronous orbit, so basically a polar orbit. And yeah, we're quite excited by that. And it's currently out in America. This is Unicorn 2D. So Unicorn 2D is also integrated in deployers out in the US when on the rocket to go. This is a much smaller camera. So you can see in the picture there, we basically built a satellite in about a week, essentially. So this was basically almost a spare parts satellite. We had some space, some customers didn't make it in time, so we decided to build another Unicorn and put it in the pod. And that's one of the great things about being a rideshare aggregator is you can do these sort of things. Much lower resolution, but really the idea for this satellite is to just see what we can get on a big scene, so big swathe width. So we're 640 kilometers by 480 kilometers and about just under 200 meters per pixel. So still would be higher resolution than VIRS, but not really super high res. But the great thing about that is you can see like a country or you can see a large region. And that too is currently in a pod out in America. So here's like another satellite. So A and D are out in America, and they've been built. 2E is the next satellite that we're working on. Essentially, that will be similar to 2A from a specs perspective. So it's going to be 24-meter GSD, so same lens. We'll probably change the sensor to be more sensitive to low light. We're still playing around with what exact sensor we'll use in the final commercial operation, and we're trying different things on these tester satellites to see what works best. And I'll explain a little bit of the timeline in a second, but that's basically where we're at. And yeah, obviously similar specs on the resolution and sway width to 2A. And that's currently under development internally. So expect to hear more news about that in the near future. The cool thing about Unicorn is they're very small satellites, and actually they all fit within a tray. So we actually have, I think, 20 trays in-house. We actually have licenses to fly 20 Unicorns out of Germany through our subsidiary. And so we're ready to go in pretty much all aspects of the business to get into service. And this is within our clean room. You can see different parts and whatnot, all the components. Yeah, essentially we've been able to demonstrate monthly production rate, which is of 1 spacecraft per month, which is really good. We also build ground stations as well. So we actually built our own ground station, which is currently going through testing just now. But as you can see from the picture, it's essentially a 2-meter dish on a platform. The platform is essentially a trailer, which is fully autonomous. So we can essentially tow it to some location anywhere on the planet, leave it, and as long as there's, it can see the sun at some point in the day with solar panels, and there's some sort of backhaul network, like a 3G, 4G network, we'll be able to talk to the ground station, which will ultimately talk to the satellites. And the first Earth stations in Germany. Hardware. So this is within our clean room. This is some happy customers from one of our early launches. Yeah, so we have all the facilities in house, and if anybody happens to be in Glasgow or in the UK and they're into NightLights and they want to come see a satellite factory, then just hit me up or hit Greg up or someone at Alba, and we'll be happy to show you guys around. Obviously, when COVID allows that to happen, and yeah, we'd be really excited to show people, you know, where the nightlight images actually come from. So yeah, timeline to service. So basically, we're shooting for June flights for A and D just now, so that's tracking fairly well, and all the hardware is gone for that. December would be the 2E flight. And that would be another sort of upgrade on the existing platform. And I can come on to a sec about like what we're doing for the early access to that imagery. And really from early 2022, we'd deploy Unicorn 2F onwards. So really the goal there is to launch a bunch of unicorns ultimately. How many is still a little bit TBC. It sort of depends a little bit on the market demand. And just generally, you know, obviously, I mean, it's largely market demand at this point. You know, if there's demand, we can, you know, fill that up with, you know, as many unicorns as required to give the capabilities. And yeah, ultimately, our longer term goal is to really build a big fleet of Earth observation satellites. That's kind of where we're moving towards as a company. And we think that technology is getting to the point where that's going to be really important moving forward. So we're targeting early 2022 for commercial ops for first images to customers for NightLights off a Unicorn. So the capabilities of the service, basically 25-meter GSD. So I think we're pretty comfortable on that now. We've got a lens there that does the job. So we're quite happy with that. Spectral bands, initially it will be RGB. We are really open to adding more. That's something that we're totally open to. I think for our point of view, we're just trying to calibrate the market interest. So if people say, hey, you know, I'm willing to pay for this band, like I really, really want it, then the great thing about us is that we're vertically integrated. So, you know, we can go modify a satellite, you know, within a couple of weeks and then get that on orbit, you know, within a few months. So that's kind of the cool thing about with us and the way we're set up. Image size will be 62 by 48. Coverage, so initially it'll be a tasking based system. Essentially we're tasking initially because we're downlink limited. We don't have enough spacecraft to do the full Earth, say once a month, like the VEER system. And also we have a lot more data because we're much higher resolution. So there's even more like sort of pressure on the spacecraft. So that sort of creates a kind of a tasking bottleneck. So basically it's going to work on a kind of first come first serve basis with customers and a queue and stuff. And I can kind of explain a little bit about that. But our aspiration, assuming there's market demand and we can reach that, is to move to monthly global composites at 25 meters. That would be really a goal that we're trying to shoot for. I think we're still a little bit unsure about the market demand for that. So certainly, absolutely, having early adopter customers is like super important for us to go build that. So certainly, if it's of interest, then let us know. The use cases initially we see is really just cities. So we see that that's really going to be like what the unicorns are probably best at. So small scenes, high resolution than what's out there. And eventually we move towards the bigger ones. Now, obviously we have something like Unicorn 2D who can theoretically do these bigger scenes and lower resolution. And if it turns out that people want that as opposed to the super high res stuff, then obviously we might change the sensors to go the other way. So we're really just sort of driven by what people are willing to go for and actually buy. So yeah, so obviously we'll let the market decide on that one. But this is our initial thoughts. And eventually, obviously, we want to be able to do everywhere at 25 meters once a month. So this is our provisional pricing model. This is essentially just like sort of rule of thumb and something that's obviously likely to vary. But initially, our main problem is going to be just tasking. So we're working on a $1 per square kilometer model. So an image would be approximately 3K US. But obviously that isn't for like the full Earth. Like as people want more, we're gonna there's big price breaks the more we do, obviously. So this is just like to get early adopter access. I think we're around the sort of 10 images a day to 15 images a day on the current downlink and the current ground station setup. So we are quite limited on how much we can bring down, and we also have to bring down telemetry and you're going to have like cloudy images and stuff. So the total useful imagery on the earliest satellites will be really constrained. So that's basically why we're doing sort of an early access program. So basically folks will be able to essentially like stick their space down in the queue. So if people are interested in this and they're like, hey, I really want to, you know, get some higher res NightLights data, and you know, I'm willing to wait to 2022, then essentially we're doing it on a first come first serve basis. It's a 10k euro down payment, and it's fully refundable, and basically that secures your space in the queue. So what we've done just now is that we have a tasking list essentially internally of objects of interest, and essentially there's going to be a commercial version of that where once we've run through just some early calibration, it'll essentially be a first come first serve basis. So if people want to, you know, image their object of interest, whether it's Syria or Myanmar or whatever the region is for whatever reason, then obviously this is how we're running it, and that would be for the first 4 images essentially. We will do price breaks as people buy more and more quantities, and we bring on more and more capability. So if that's of interest, then we have a website, and people can reach out to me personally, and I'm happy to chat to them about that. And yeah, that's kind of what we're looking at doing. Future NightLights workshops. So yeah, basically, the whole idea for this actually came. We wanted to do it in person. This came from pre-COVID times. And there was a plan to do a very basic plan to do it in person that never really got that far. yeah, essentially we would like to do it in person down the roads. It seems like there is quite a lot of interest. I mean, I've been looking at the numbers, and we're probably like 60, 70 people on the stream. So that's it's a decent audience for sure for the first event. And we're hoping that there'll be an annual event where next year we'll be able to widen the audience some more. And yeah, hopefully there'll be more use cases, more satellite imagery coming on stream, and yeah, really just more things happening in the community. That's kind of like what we're hoping for. We have a Twitter account as well, so I'm sure some of you guys and girls are following it, but that's where we've been sort of tweeting updates and things, and just trying to let people know what we're up to. And yeah, I think that's pretty much all I've got. Like I said, people can drop me an email, just Tom at Alba Orbital, if they want to chat about Earth observation data and imagery and things like that, and specifically nightlights. But yeah, that's pretty much all I've got. Don't know if there's any questions, perhaps, Greg?
Yeah, I've got quite a few questions. So, so for Christopher Kyba asked, I don't understand how you deal with cloudy cases. So it's 3,000 for a tasked image, or do you guarantee a cloud-free scene for 3,000? Yeah, so we won't sell cloudy imagery. So we'll just keep on taking shots until it's cloud-free, basically. So so yeah, yeah. Obviously, we'll have to determine what exactly is cloud-free, because it's very hard to get 100% cloud-free. So sometimes you maybe get like a 5 or 10% cloudy image. So we still need to figure that one out. But it's a totally valid point. Like, our goal is definitely not to sell, you know, cloudy imagery. So I think we would just basically work with the customers on, you know, obviously if people want an image of a location under clouds, and Glasgow is a good example of this. We're very cloudy here, unfortunately. We just have to obviously wait until it clears. That's pretty much what we could do. So obviously there's a trade-off on like the time of month for different locations. So yeah, I think we just kind of like, you know, play by ear with the customer and see what works. But absolutely the goal would be to try and get as cloud-free images as possible, and not sell people cloudy imagery, because that would suck. So we're not going to do that. Okay, and we're kind of running out of time, but see if you can answer some quickly. Jan Peter Muller asked, what would be the duty cycle? How many images per orbit for nightlights to begin with? Yeah, the duty cycle and how many images per orbit. Yeah, I mean, we're really downlink limited. So we're probably on the sort of 15 images a day sort of range per spacecraft, or certainly 2E is in that order for the high res ones. 2E will hopefully be more than that. And as we deploy more ground stations, we actually double every time we add another ground station, we essentially double the throughput of the satellites. So it's kind of hard to say exactly, but certainly if people are looking for cities in some sort of semi-regular cadence, we should have capability to do that. If people are looking for countries and regions, that's going to start taking up pretty much all our capability with one customer. But the goal is to add more unicorns as we have more demand to satisfy that, and that's the goal moving forward. Okay, and Brian Min asked, what is the plan for sample imagery from unicorn, and what is the sensitivity? Yeah, it's a good question. I think sample imagery, so we already have like a kind of task list basically internally of objects we want to look at. So as soon as we get up in June, we're going to start looking at nightlights objects. It sort of depends on time of the month and location, but we're going to probably publish some sample data. I'm not sure how much, probably within the first month or two, hopefully, assuming everything goes well. And we'll put that out there, just public domain, and people can assess that and see if they like it or not. And then from that, then obviously that's, you know, we don't want to use up too much downlink on just the sample stuff, because we think we've got a bunch of customers we need to sort of keep happy as well. So in terms of the sensitivity, that's a great question. And really that's why we're trying different sensors, I think, is the reality. So we're trying to figure out like what sensor will do what and what that might look like. So we've got, so A and D have slightly different technology in imaging sensors, and 2E will have a slightly different one again. So by 2F, we have tried a few different techniques basically. And yeah, I think just to add to that as well, we have a theoretical value for the sensor in 2E, which is 600 millivolts per lux, but we really kind of want to like run some experimentations on the ground after we get the sample imagery, so that we can give more accurate values rather than just relying on the data sheet. So it's still a bit TBC at this stage. One more question. G. Lee asked, will Alba Orbital provide a radiance calibrated image product? I would assume the answer is no initially, but potentially in the future. Is that right?
Yeah, I mean, I think like we're just really focusing on getting just images in the short term, and obviously we want to make it, we want to make the product better over time. And I think that is something we could do down the road if there's enough demand for it, basically. I think we're just trying to figure like what is the demand. Like some people come to us, be, hey, I really want this band, and like, but like if it's just like one person wants that band, whereas 100 people want RGB, then that's what we're trying to get a handle on is who wants what and how badly do people want that, obviously, and where do we stick the satellites,
And one final question from Ran asked, how much time do you expect will be needed from tasking to image collection?
That's a good question, Ran. How much time will be needed? Well, it depends, obviously, like when people want to image in the month, because obviously some products are really driven around the moon cycles. And obviously it's the weather. But yeah, theoretically, we can do it within a day. That's the sort of the hard physics limit. I think in reality, it's probably going to be a few days. Is probably the reality on the early ones. Eventually, we plan to really get that down to below a day and even quicker. But and the other thing as well is if we know people's targets up front, if they're trying to do like say monitor our city over a year, say COVID spread over a year, and they want to see that, if we know that's happening, we can tell a satellite that's what it's got to do basically, and we can pre-task these things. Yep.
All right, cool. I think we should move on because we've ran over a little bit.
Sorry about that.
And thanks for everyone's questions as well. Awesome. Next up, we have Travis Longcore from UCLA. Hi, Travis.
Morning, everybody. Share my screen here. So this is from the technology to the use case. I want to share some work this morning, well, morning for me, that we did about the National Park Service units in the United States, with the idea of looking at their light pollution profiles as a guiding principle for management. And I want to add that this was, despite me putting together the presentation and presenting here today, this was all work that was done and predominantly led by undergraduates. Harrison, Shan, and Ben were undergraduates when I was at the University of Southern California, and did this as part of undergraduate research and demonstrating use of the data. I'm now at UCLA, University of California, Los Angeles. So of course, the National Park Service in the United States has a night sky team and has been building a considerable amount of both programming and science around the nighttime portion of parks. Series of posters produced by Tyler Nordgren talking about half the park is after dark. And so I was thinking about this and wondering about the way in which one would go about knitting together programs and perhaps educational materials across different parks, management strategies to achieve a goal of night sky protection, and to address all the many impacts of light at night, the ecological, the cultural, the aesthetic, and astronomical impacts. And so I was looking at the units by which the National Park Service manages its territory. And these are, I've cobbled together a quick map here. The Northeast, the national capital, which if you aren't unfamiliar with the U.S. Park Service, they run most of the what you would think of as being city parks in Washington, D.C., the site of recent events. The Southeast region, the national trails, which is sort of an overarching set of territories that extend across many different regions. The Midwest, the Intermountain, so that's the big parks in the Intermountain West, Yellowstone, for example. Pacific West, which also includes Hawaii, and then Alaska. And these are the units by which the Park Service organizes its property management. And so the underlying question was really, is there another way that categorize these units that emphasizes similarities in their nocturnal environment? And how could this and nighttime remote sensing aid in development of light pollution mitigation approaches? It's a bit of a blue sky kind of question. They didn't come to us and say, hey, we'd like this question answered. This was an idea of wanting to look at these data and figure out what those similarities were, whether the geography makes sense or whether there are ways to see links between parks that share common challenges that maybe could be addressed in common ways. And so this is the workflow for the project, which is basically consists of using the VIIRS day-night band as processed by Elvidge's group and projecting it to an equal area projection. Then getting the National Park Service boundaries and creating buffer zones around them, because the question from a light pollution management perspective is not only what light is within the parks, but what about the areas surrounding it? And on the theory that nearby lights are potentially more damaging than faraway lights, we built a series of buffers around each of these units. Now there's over 400 of them, and you might say, I don't remember there being 400 national parks in the United States, and there aren't. They're all different units that are managed by the National Park Service that are in addition to the national parks themselves. So these would be national historical sites, historic birthplaces, trails, national monuments. So there's quite a bit of territory that doesn't necessarily reach the everyday awareness is being managed by the National Park Service that in fact is. And so around each of these 400 plus units, we created a 1 kilometer, 10 kilometer, and 100 kilometer buffer. And I know that impacts on the night sky exceed 100 kilometers, but we felt this was sort of a reasonable thing to get a picture about the neighborhood in a hierarchical way around each of these units to be able to compare and contrast them. We then overlay these in ArcMap, and actually early on we did this, and then we switched to a approach using QGIS and batch processing. And calculated the upward radiance in each of those areas, and then used Ward's method hierarchical clustering to create a series of clusters where the parks shared the maximum similarity within all these buffers and over all months. So we actually did this on a monthly basis and this I'm reporting here, I think we have 48 months of data in this particular analysis here. The other side benefit of doing this is that then we have now a time series of upward radiance within each National Park Service unit and within buffers around it. So we can start to track and give insights about individual parks in terms of what's happening with this particular data set. And with all of its benefits and with all of its limitations as well, that I'm sure others have discussed here today. And as I look at this seems pretty simple. It took quite a bit of time. There's quite a bit of data management here, and also a bit of heartbreak and anguish over getting small complex units to extract the data from the raster. So small polygons in either, especially as we were working in an arc map, we would get a lot of failures just on implementing this workflow, and had to figure out what was going on, why it was we were getting those errors. And it had a lot to do with these small complex park units that either were smaller than a pixel, so we had to give them a buffer, or other had complex geometries that just failed, to be quite honest. So we finally got around. We tossed some of the very, very small parks in Washington, D.C. for this reason, but ultimately got a data set of 48 months of data. And this sort of was the first test to figure out, well, you might think that these things correlate with each other. And the fact is that they do pretty highly. So the numbers going across, these are correlations between the light from within each of these parks. That's mean 0, that's with no buffer. Mean 1's 1 kilometer, 10 is 10 kilometers, and 100 is 100 kilometers. And I recognize that people are going to be upset that we've averaged it, the upward radiance, it already being by area, but didn't see another way to do this. And the interesting thing is that there is a high correlation between upward radiance within a park and a kilometer around it, pretty high, but it is not that high a correlation once you get out to 100 kilometers, which means, of course, as you might imagine, that parks are in very different contexts across the country, and this could be a reasonable means by which to investigate them. So here is getting to results, here is the upward radiance, mean upward radiance within each of those units that are the current management units for the National Park Service. The one in the middle that has the largest numbers, that's NC, that's National Capital. The Northeast has quite a bit more, that's NE, Midwest. IM is the Intermountain region, AK is Alaska, and PW, Pacific West, and SE, Southeast. And at the end of the day, maybe the regional variations are better as a way to there are quite a bit of similarities between them, and they're probably doing all right, but we'll go down this route. We then created our own set of regions of parks and described each individual park within a series of classes that I'll get into in a second. We called them near bright, remote, standard, suburban, urban, and light saturated. There is a slight improvement here, and I'll have to present this to the Park Service and see if they find the usefulness out of it. But it does give us a way to kind of think about the context in which these protected areas, or in some instances, the national parks are very much protected areas. Others are very urban. Grant's Tomb, for example, is basically an urban park, as is many of the national capital situations. So we clustered those out and then described them. So our idea of a near bright park, these are parks that are have very little upward radiance within the park itself, but are very bright at 10 and 100 kilometers. And the example I'm showing you here is the Santa Monica Mountains National Recreation Area, which is in Los Angeles. I'm actually sort of sitting right about there. And the interesting thing is the park, or the recreation area itself, which is a combination of federally owned land, state-owned land, privately owned land, and includes even some includes residential neighborhoods within it. But within that, it's got a reasonable area of low upward radiance, but it is next to an incredibly bright city. And so we see that as being similar, and there are other parks and units that are classified this way. For example, the Indiana Dunes National Park, which is near Chicago, is a very similar thing. The park itself doesn't have a huge amount of light, or very little light within the park itself, but it is near an incredibly bright location. So these are the near brights. Remote, this is sort of most of what we would think of as your typical national parks, the ones that you would have the most recognition as being part of the national park system. This is Zion and Yosemite and Yellowstone, Sequoia, Petrified Forest, Olympic. And they have very little upward radiance within the park and low upward radiance within 10. And usually as you get out to 100, you get regression to the mean in some, but these are the ones that have the most, I would say, astrotourism and are the best skies within the national park system. And now we have a list of those that all sort of meet this criteria, and we can cross-reference that with the monitoring that's done on the ground. Standard, and of course we can compare it with the World Atlas of Artificial Night Sky Brightness, which is another way to go about this assessment. Standard, these are low light within the park, but sort of average within the 10 and 100 kilometers. So things like the National Military Park in Arkansas, Channel Islands National Park in California, which has low light, it's on the islands off the coast here, but at 10 and 100 kilometers is quite bright because again, it's dealing with Southern California lights within its sphere of influence. And I should mention the reason that I thought that this could have additional utility outside of simply taking the World Atlas and doing those calculations is the location of the brightness. Whether if you had something that is within a particular region, it's sort of out from the park, it suggests different kinds of approaches from a mitigation. If there were incredibly bright things in the 1 kilometer outside a dark park, then emphasis would need to focus there. Similarly with 10 kilometers, with 100 kilometers, then we're talking about regional policies. And so this was a way to sort of get at some of those influences and what the challenges are from a policy perspective of parks trying to manage and protect dark skies, of where to put emphasis going from the park to a kilometer to maybe they're right outside the park, there are vendors or park associated tourism facilities that could be approached or at the 10 kilometer range versus needing and pursuing regional policies at the 100 kilometer range. Hence this approach. Suburban parks, moderate levels of park within it, moderate light within the buffers. And this is one of the eye-opening things about doing this is that despite the view of our national parks, there are a lot of units that are in these suburban and then of course also urban contexts where it's bright within the park, bright surrounding it. The Lincoln Memorial in DC follows in this sort of moderate within and surrounding. And then our last category were these light saturated ones that were just actually some of the brightest things on the landscape, mostly in Washington, D.C. Our White House is lit up far beyond reason, I might say. So those are the categories. And I sorted out the actual national parks here by the 2 categories that they fall into, which are the remote and standard. And you can see the standard, the 100 kilometer buffer is over here on the right, and it is the ones that have the higher, the blue bars. A lot more light at the 100 kilometer brings you from being a remote park into the standard category. So for example, up here we have Channel Islands National Park, which is very little upward radiance from within the park itself, but quite a bit from within the 100 kilometer buffer. So its challenge, of course, is keeping these numbers down within a kilometer and 10 kilometers, but has this regional challenge of just where it is. Hawaii features here with the lowest light at all of these. Dry Tortugas, of course, is an island off of Florida, so it has quite a bit of an advantage. On the mainland, Big Bend National Park has the least light within it at the buffers and within 100 kilometers. Death Valley, also very well known. Canyonlands, Grand Canyon, Great Basin, Redwood, all familiar dark sky locations. And then we pop out these ones that are getting closer to major light sources. So Joshua Tree pops out here, and Kings Canyon, Carlsbad Caverns. And so what we're suggesting here is that these parks have some things in common that perhaps can be shared and have shared management approaches as you go across it. And then some of our brightest one, Wolf Trap Farm Park, is pretty bright, and also is a pretty large visitor serving facility on it. So this isn't entirely surprising. So there's a whole list here, and then if we were to go through the whole 430, we can now rank these by within park light, surrounding, and these buffers. So just to talk a little bit about some examples, the time series that then come out of these, and I should, speaking of time, be looking at the time, make sure I'm not going over, is the Mediterranean network here. Again, this is Los Angeles. These are the Channel Islands National Park that I just mentioned. This is actually Cabrillo National Monument down in San Diego. And so we have these time series to look at, and can extract more of these data and add it to. You can look and see the interesting thing here is just how much higher the average radiance is a kilometer out than even 100 or 1 kilometer. Of course, at 100 you get regression to the mean, but at 10 kilometers there's something really fascinating going on there on a seasonal basis. That happens to be a tomato greenhouse that's in an agricultural zone just west of the park that comes on during the winter time when they're doing tomatoes. And we have complemented this with a transective ground-based hemispherical imagery. This is an area outside of the recreation area, but about a kilometer and a half, 2 kilometers from that the tomato greenhouse that causes the sky to glow yellow. The one on the left is a 30-second exposure when that greenhouse is not operational. That's about 20 millilux scalar illuminance as measured with a sky quality camera. And then on the right, there's more cloud cover, so that's influencing it, but that's a 15-second exposure and 80 millilux. So there's about 4 times increase in the ground-based illumination with that greenhouse on versus the greenhouse off. And so that suggests to, and I've shared actually this with that park, that there may be some outreach needed and some policy needed relative to the operation of greenhouses in facility in vicinity of these facilities of the National Recreation there. This is Channel Islands National Park, so this is off the coast. Again, we describe this as a standard park because there's so much light in the 100 kilometer, but there's also here quite a bit of variation at the 10 kilometer area that I wasn't picking up in the long term of the veers. A little bit of an upward trend as well in the within park 1 kilometer and 100. And so we had a look at that, and this is a work that another undergrad did, Eliza Gutierrez-Dewar. I just want to show it. This happens to do with the fact that there's a commercial squid fishery that uses light-induced attraction of the squid to the surface in order to get them. And we did another analysis using some data provided by Chris Elvidge and his group, looking at this park. So the islands here are Santa Cruz, Santa Rosa, Anacapa, and these polygons are actually areas of marine protected areas where we're not supposed to be fishing. And these are the density of lights, point detections and their brightness using a point detection algorithm out of Elvidge's lab. And looking at that, and so these are squid fishing locations. Every one of these spots here is a squid fishing location, and it's a seasonal fishery, and so that explains the lights changing over the course of the year. And we also saw a dramatic increase over the time period. If we look at the yearly change, this should, yeah, so you can see we're looking up here within this circle. This is the Southern California coast, and you can see the movement of those squid boats over the 4 seasons. So this is going from spring, summer, winter, from fall, winter. And so they're moving around there. And also we looked at it over time and they're increasing. So it sort of really draws out what's going on this park by looking at the buffer around it and the temporal changes in the veers that then, through this separate analysis correlate with, and we can confirm is really being driven by this light-induced squid fishery. And And so this is what that looks like. This is a picture that Bennett, one of my co-authors, took getting the data out on Santa Cruz Island to compare with the satellite data. That's a squid boat. That's one boat illuminating the shore there, and leads me to sort of question about this is maybe that each park is unhappy in its own way. To paraphrase Tolstoy, there are all these interesting issues that are going on, and looking at the data this way perhaps give us a way in to connect up the remote sensing to on-the-ground phenomena to management challenges. And in this instance, the management and impacts from the squid fishery, but other things in other parks, but also to share similarities, educational materials that might work for the Santa Monica Mountains National Recreation Area near Bright could also be applied in other near Bright parks where you've got the ability to get away from some lights and some astronomical observation, but also the incredible challenges of being near a light polluted landscape. So I wanted to share this just sort of as a use case and a demonstration of the value of free and open data, to be quite frank. The ability to access these and set them up in a workflow and get a lot of them is only possible because these are free data. And also that it starts to build the next generations of students interested in this topic and going on to further work on light pollution topics as they proceed as well. So with that, I will end and available for questions if there's a way that they get to me.
Thank you very much, Travis. That was great. I don't know how any questions, and so far Ran has put in the chat that about a relevant study that's published on the impact of using birds on the impact of COVID on protected areas, so that might be of interest. But as we've run a little bit over, it might be best just if anyone has any questions for Travis, they can put that in the chat and you can answer them in there. All right,
great.
Thanks very much for joining us, Travis.
Thanks for having me.
Next up, we have Guy Thomas, who I think is already here.
Am indeed. Stand by. Sharing screen now.
Thank you.
I just had it up. Where is it? Right here. Let's see. I believe you have it now, correct?
I don't think we do. There's a share screen button at the bottom.
Yeah, I touched it. Let's go back and see. Try again. Had a little trouble the other day too. Share sound, yes.
All right, I think it's coming up now.
There we go. You've got to hit two buttons. I forget that second button, even though I've done this several times. From the beginning. Okay. I'm a little different. I am not a light professor or researcher in any way, but I did invent satellite AIS, and a couple of people have mentioned how they're using it, and that's why I'm here today, to talk about where we're going in the extension. Once I invented satellite AIS, almost immediately 10 different organizations from 6 different countries, Canada, Norway, Germany, France, Italy, and Japan, all came to see me and said, we're building imaging systems. Most of them were SARS, but some of them were optical as well. And we'd like to partner with you, collaborate with you. So I said, yay, verily, let's do it. And sometime in late 2005, we had our first meeting on the 22nd of April of 2005. And by the end of 2005, I was very aware that a lot more was going on in space than I had any idea about it. But we came up with the idea of this: collaboration in space, international global maritime awareness. How long do I have? I have about 20 minutes, correct?
Yes, maybe a little bit shorter to allow time for questions.
Yep, okay, I'll be quick. This is about a 50-slide presentation, but no, it's a 70-slide presentation, but I plan to stop it at about 25. But if anybody wants the rest of it, which goes into all these different sensors in some detail, you're welcome to it. Anyway, we originally looked at this as a security problem, but then the more I found out about it, I'm an ex-Navy security person, and I flew with the Air Force too. I realized how very important the maritime environment is and its resources, maritime safety as well. And so I actually reversed it. But it was obvious to me that we needed to form a global space partnership.
We're also going to be talking about.
And basically how I got involved in this is on the day of 9/11, the president tasked, I was a research professor at Johns Hopkins on loan to the Naval War College. And on the day of 9/11, the president tasked the head of the Navy to look at what our vulnerabilities were to maritime terrorism, and what we could do about it. It came down the chain of command and landed on my office mate's desk very early the next morning. And he tasked me at about 8 o'clock in the morning of 9/12, the day after 9/11, to be his technical advisor because I had significant experience both in wargaming, and we held a series of war games, and in maritime sensors. This is what we came up with. This is what we look like, and this is what we came up with. We could define every bullet here. This is not just a pretty picture. We actually ended up writing a several hundred-page secret document that we couldn't get anybody to read until we put this together. And you'll notice up here we have commercial satellites, and I will go into that. Also in that time, I became aware that the Coast Guard had the AIS system that they were going to put that would go out about 25 miles. But the last several years of my time in the Navy, I was a space operations person, and I'd also worked on our president's airplane. And I was pretty sure that I knew how to put a receiver in space. So I spent 3 years begging people for money before I finally found somebody. I found people that liked my idea, and I found people that had money, but neither one liked my idea and had money until 2004. Anyway, that led directly to my writing this task in our national space policy. It says that we will basically build, using international collaboration, we will build an international system to enhance safety at sea, mutual security, protect the environment, the resources of the sea, the flow of commerce, blah, 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 blah. It's never been implemented. I spent 9 months working on that, and I literally had the attention of Chief Staff of the President of the United States, Barack Obama, and then Chief Staff went off to be the mayor of Chicago, and I lost my friend in court, and it's never been done. It still needs to be done. Background, I became the Science and Technology Advisor for Maritime Domain Awareness, basically in October of 2001, but before it was even created, but they created the post in 2003 and gave it to me, and I became, but we looked at the official person. We looked at every platform, every sensor, processing system, fusion system, analysis system, display and decision system, and dissemination system, also known as comm system, we could find. But as I said, by late 2005, it was obvious to me, even before that, that commercial space was going to be a big core of this. I'm still doing that research. Basically, I've had to explain a lot of people that they mix up these terms, but this is the way I define it. You have data, you collect it. You have phenomenology, you collect it. You process and fuse it to make information. You analyze it to become knowledge. You use display and decision aids to give you a decision, an understanding of it. And hopefully your leader gives you wisdom to do that. The desired end result of all these, in my case, is what I call global maritime awareness. Why global maritime awareness? Fair question. Why is it important? Even more important question. Maritime security is essential to every nation's well-being. Even though you may not have a coast, it is very important globally. Maritime security is directly proportional to what your maritime situation awareness is. I don't just say that, I've studied it now for over 20 years. Thus, MSA equals MS. And this is true globally. It is not just true for those of us that have seashores. Ergo, global maritime awareness means a more secure world. That's why it's important. And that's why I'm talking to you guys. I want you to know this. I need your help. Help. Advanced numbers of capabilities of the unclassed systems. You guys are talking about some of them. You all know that. The new radar satellites that are coming on board, the RF geolocation satellites, the imaging systems that have now been up there for 30 years. They're all very important, every one of them. We also, you probably know, if you're, and I'm sure this audience does, some don't, that there's been an explosion, a major avalanche of what's happening in data processing. It does offer the world an opportunity to build an excellent global maritime awareness system, thereby significantly improving life on Earth. Now, any of you guys that know anything about the United States know that what happens in Las Vegas stays in Las Vegas. It's the fun city. But what happens in the world seas has an impact all over the world. It impacts our safety, our security, our environment, economic, and resources. Global collaboration is based on trust. It is required for global maritime awareness. You can't serve trust. It needs to be earned. Mike Muller said that when he was the chief. He and I were friends when he was a captain and I was a commander. But he basically has said this at the when he was our head of our military, and it's very true. Unclassified space is what I'm going to talk about. Marine term is bluff. Not I'm going to fake you out, but rather bottom line up front. Let me give you the numbers and then what they mean. Currently, right now, there are Earth observation in space that assist with this situation. I added night lights for you guys just for this brief, by the way. I did have 6. I did have 5, now I've got 6. Satellite AIS. And we have comment system arriving soon as well. There's the first comment, truly comment, both electronic intelligence and communication intelligence satellite is literally being prepped for launch right now. It's called Amber. It's built by Horizon Technologies. Satellite AIS, there's about 12,000 satellites going to be built. Something like 1,000 of those are going to be focused on Earth observation. There's about 175 up today. I think it's going to top out in AIS for around 250. I sent you guys a question, but you didn't read it. Is there any way we could put an AIS receiver on your unicorns? That seems like a good idea to me. And there's a market out there. I can talk to you about it. Synthetic aperture radars. There's about 20 up there today. It looks like it's going to be 150 in the next couple of years even. Optical, right now there's about 80 in the low 80s. I'm including the VIIRs in that system. Video, there's 4 up there today. SIGINT, as I say, there's ELINT. There's about 6 ELINT satellites up there today, and there's going to be, there's 8 up there today, I'm sorry. It looks like to me that we're going to have about 50 SIGINT satellites that I know about. Also, I included the machine-to-machine and the Internet of Things satellites because they're going to be fully exploitable. They're already semi-exploitable today, but they're going to be fully exploitable very quickly. And there's a lot of information that goes back and forth from sea on the M2M systems, machine-to-machine communication systems. Wrote a paper several years ago now that I call Space-Based Maritime Situation Awareness, where 3 global comments converge. It's another way to look at it. I think we all know that there are 4 global comments. The maritime comments, which is in fact about 2,000 years old. Air, it's about 120 years old. Space, which is something like 60 years old, if you count the start at the launch of Sputnik 1. And cyber, 10, 20 years, something like that. Pick a number. It's grown to, it's dramatically expanding even today. Major advance in the last 2 have had huge effects on the MSA. By the end of the 20th century, we all know it's an interconnected world. Most people do not realize that it was not connected in the maritime domain at all, not very much anyway, until 2008. Satellite AIS has changed all that. Provides the needed location identification missing in the maritime domain. Maritime situation awareness is needed for counter smuggling, drugs, people, arms, goods, counterbat, and to counter piracy. It's a big problem. Didn't used to be, but in the last 20 years, it's dramatically increased. Maritime safety would be assisted dramatically by situation awareness. Environmental protection, I've said all this. The other two that I haven't added before that is disaster mitigation and disaster recovery. One of the very first uses of satellite AIS after we got it up in 2008, the Haiti earthquake, and they used satellite AIS to know what disaster relief was going to arrive when. They only had one berthing space, one place where you could pull across up to a pier in Haiti at that time. So it was very important that they prioritized what was landing first. I think water landed first because their water supply was compromised. But that became a major thing. That's a major thing they do today right now. They've figured out ways to use satellite AIS to dramatically assist. Basically, it's feasible to use one center for the global coordination of all space centers. The Irish National Space Center was going to do that until they lost their funding for it. But we're still looking for someone to do that. In a meeting, I've been to many NATO maritime security meetings in the last 15 years. One in April 2016 was on how do we establish global maritime awareness. It basically was on maritime domain awareness, and they said it needs to be done globally. We need to coordinate and synchronize. We need to develop command and control procedures to coordinate. We need to develop linkages between all the different maritime domain awareness, maritime situation awareness organizations in the world. We need to get leadership and vision, and I think they've got that in a Commodore in the British Navy called, interestingly enough, no relation to me. His name is Thomas Guy. I go by Guy Thomas, and it's kind of funny. Some people originally got the two of us confused, but he's a rear admiral in the British Navy now, working for NATO. He has the leadership of the vision, no doubt about it. We need to provide a focus. We need to collaborate both regionally and globally. There's already some regional organizations out there. We need to link them up today. Goes way ahead, use the development of space-based MSA to develop what I call worldwide global maritime awareness. This is something I came up when I was first working on this. It was obvious to me that Karl Marx had the right idea, just the wrong execution. In the maritime world, it's each according to its ability, to each according to its needs. There's a lot of countries out there that really have huge needs. Africa, South America, Micronesia, South China Sea, Indian Ocean, places out there where the people are dirt poor, but they really need to have better MSA, and space will give that to us. Basic four types of satellites. I've already talked about these already. Each makes a unique contribution. You have to have all of them, especially the first two, satellite AIS and synthetic aperture radar. Now the SIGINT systems are coming online too. They're going to be very important. And I'd be happy to give you a brief on why that's important, but trust me, they're going to be very important. But people say, well, it costs too much. Actually, if you look at patrolling the oceans of the world, space systems are very cost effective. They make the terrestrial systems, the ships and planes, many times more effective by allowing them to do a much better job of pinpointing their search. It's a huge saving in fuel wear and tear. The game changer is satellite AIS. It makes it both viable and feasible. It's the most significant change, people tell me, in maritime operations since the screw propeller, maybe the radar. Significantly more effective than GPS. GPS has had a huge effect all over the world in many different ways, and it's certainly had an effect in the maritime world. But satellite AIS is changing the maritime world at its core. One of the other things that I let people know is you really did need to develop, and this was back from 2002, you need to develop a common distributed virtual database, information extraction and exchange system. You need to take it across the whole link that I put out at the very first of this brief. This was how we planned to defeat the Soviet air defense systems. Each of these was developed. That was this one by the Navy, this one by the Navy, this one by the Air Force, this by the Army, and this by the Army air defense people. You spend $105,000, $105 million figuring out how to come down this in lightning speed. We need to do the same thing in the maritime domain. And yes, I need to color one of these blocks black because yeah, there is some black information out there, classified information. But the vast majority of this is unclassified. This is the name of some of the US databases, but in fact, there's a cloud out there in the maritime world that is full of databases and information exchange capabilities we need to harness. In fact, I wrote this, as I say, in 2002, and I also said that we needed smart agents, artificial intelligence, machine learning to do this in 2002, and this is what they needed to focus on. There was two different companies that rose to that pitch, one of them headed by Jayton Baines and the other Paul Krastansky, and they have solved that problem, but that was in 2004, 2005. They're still working on it, and other people are too now. I call that dynamic data analysis now. Basically, you sense it, you process it, you fuse it, analyze it, goes back up, you decide, and you act. And that's my brief, my friends. As I say, I have literally another 40 some odd, 47, I think it is, slides I'd be happy to go with, but we don't have time today. Be happy to talk to anybody about this. Over to you, sir.
All right, thank you very much, Guy. It was great to have you on. Just seeing if any questions are coming in. I think we don't have any so far.
I'm crushed.
I know.
I was hoping I'd be deluged. Of course, the question I'm really hoping to hear, the question I really, really hope to hear, and I'm sure you will all understand that, is where do I send the money?
If only it was that easy. Yeah. But yeah, thank you very much for coming on. Great to have you.
Right, great to be here. And it's that picture up there in that corner is the first cruiser I served on back in 1968.
Amazing. And Mark has just written in and said thanks. It was a very interesting topic.
Sure.
Okay. People are loving it.
They're good.
All right.
Right, Ron. Thanks.
Thank you.
Cheers.
So next we have...
you know how to reach me if you need me.
Perfect. We have Ran up next from New Light Technology.
Yeah, I'm unable to share my screen.
Okay. So, sorry.
Because the other screen is still shared.
Okay, hold on. Just be a second.
No, the other participant is still, yeah.
Yep.
Okay, so good afternoon, everybody. I know that we are running a late, so I will try to run over these slides as fast as possible. Today we heard a lot about many great applications that rely directly on nighttime lights. In the next few minutes, I want to show another application of nighttime lights directly related to urban research. And the method that I will present uses nighttime lights as a source for reference data to map urbanization based on Landsat daytime imagery. So as you all know, urbanization has been a fundamental trend of the past 2 centuries and the key force that shapes many dimensions in our life. In 2007, for the first time, more people lived in urban areas than in rural areas. Today, 56% of the population lives in cities, and by 2030, it is projected to reach 68%. So the question is, what do we really know about the extent and pace of urbanization? And the answer is that we don't know much. We are still unable to map in real time urbanization processes. How do we get data on urbanization? So traditional methods include ground surveys, administrative data, cadastral documents, aerial photographs, These methods are obviously expensive, time-consuming, making it very hard to monitor changes on the ground in close to real time. On the other hand, there are more and more satellites that constantly orbit Earth and collect data in different spatial, spectral, and temporal resolution in daytime, in nighttime. And they allow us to track Earth in close to real time and to convert all this data into meaningful information about what is happening on Earth, including urbanization processes. So the question is, how do we take all this data that is constantly collected by the satellites and convert it into information? In this case, how do we map urbanization processes automatically? To do that, we can use different approaches in machine learning. And obviously, we cannot talk now today about all the machine learning approaches. There are many approaches: supervised, unsupervised, semi-supervised, CNNs, and others. Today, I want to talk about supervised machine learning, which we used in this research. And the idea of supervised machine learning is that we have labeled examples. We have examples that are labeled. We want to teach a machine to learn the characteristics of whatever we want to classify. In this case, it's urbanization. And based on that, ask the machine to predict which areas around the world are urbanized. For supervised image classification, we need reference data. We need labeled data. And this is a real challenge. How do we get this labeled data? So one option is just to, just to collect data based on visual interpretation, which we did in one of our studies. We collected 20,000 labeled examples spanning India, used these examples to train a machine and to map all the urban areas in India. But this is, of course, not feasible in global scales and in real time. On the other hand, and this is what we're talking a lot about today, is nighttime light data. Nighttime lights are closely related to GDP, population size, urbanization, wealth, as we saw. And what we're doing here and what I want to present now is a methodology that we developed that uses nighttime light data to extract labeled examples, which are then used to map urbanization globally. While this procedure was originally developed for DMSP-OLS, it can easily be applied and adopted to VIRS. And in fact, we at New Light Technologies are using this method to map urbanization in different developing countries and contexts. So I will present this method. And when we're using nighttime light data to map human settlements and urbanization, we have the nighttime light data. We can categorize this data according to the DN value. And the idea is that we define a threshold. Any pixel that exceeds this threshold is likely to be urban. The question is, what is this threshold? How do we define a pixel as highly lit? There are also other limitations of DMSP-OLS as well as VIRS, the coarse spatial resolution, the blooming effect or the expansion of light, oversaturation in city centers, meaning that in the city center, there are bodies of water, vegetation that we cannot necessarily capture using the nighttime light data. So our approach is that we're using nighttime light data to collect reference data for image classification. We take DMSP-OLS, we define a threshold, and I will talk in a bit about how do we define this threshold define a pixel as highly lit. But then, as I mentioned, in any urban areas, there are also areas covered with vegetation or areas covered with bodies of water, which we want to remove from these highly lit pixels. So we take the DMSP-OLS, we mask out all these areas of vegetation and bodies of water, and we throw points on the map. If a point falls on an area that is highly lit and is not vegetation or is not a body of water, it is labeled as built up. Else, it is labeled as unbuilt up. And this is how we can collect millions of examples that we can use for this supervised image classification exercise. So again, we rely on two sources of data. One is Landsat 8, daytime imagery in a spatial resolution of 30 meters. The other one is DMSP-OLS. We use Landsat 8 to detect areas of vegetation and bodies of water. We take this data, we mask it out from the highly lit pixels. We throw the points, train a classifier, and then classify the built-up land cover in a high resolution using Landsat 8 as input. But there are many things that we need to consider. As I mentioned, how do we define a highly lit pixel? What is the threshold to define a pixel as highly lit? How to define vegetation pixels? Which inputs should we use for the classifier? Another very important question is, what is the size of the unit of analysis? Is it better to create one classifier that can be generalized and map the entire country of, say, India? Or is it better to have many, many small classifiers that are very specific and cannot be generalized, but maybe result in more accurate results? So now I will walk you through the process that we went through. So first, we take each country, and we did this analysis in the context of India, Mexico, and the US. We take each country and divide it into hexagons. We use each hexagon as an independent unit of analysis. We collect data, train, and classify each hexagon individually. And we experimented with different sizes of hexagons. Then for Landsat 8, we used Landsat 8 to detect vegetation or detect bodies of water. How do we do that? We did all the analysis in Google Earth Engine. We take the entire stack of Landsat imagery that were collected in a given year. We remove these scenes that have a lot of cloud coverage. Then we calculate a median value, representing the median value of each pixel over a course of a year. In addition to that, we're calculating additional spectral indices, such as NDVI, NDBI, NDWI, and others, which can also be used as inputs to the classifier. So now the result is Landsat 8 data, where for each pixel we have all the band values, including NDVI and NDBI, which we use as inputs to the classifier. Then, as I mentioned, one of the most important questions is, how do we define the threshold of a highly lit pixel? Because obviously, in a densely urbanized area, these thresholds should be higher than in rural remote area, because if we will have a very high threshold, we will not capture those areas in the villages, which you can see here in the bottom hexagons on the screen. So to define this threshold, in each hexagon, we calculate a percentile rank. We calculate the 95th percentile and the 75th percentile value. If the DN value of a pixel is higher than the 95th percentile value of all pixels in a given hexagon, it is labeled as highly lit. If it is lower than the 75th percentile, it is labeled as low lit. And as you can see in the maps on the right, there are variations in these thresholds. So the colors represent the threshold that was determined for each of these hexagons. So now we have a threshold to define a pixel as highly lit. We take the DMSP-OLS, we remove all the areas with vegetation and bodies of water, we throw the points on the map. Each point is labeled either as built up or not built up. If it falls in a highly lit pixel that is not vegetation or body of water, it is labeled as built up, else it is labeled as not built up. We overlay it with the Landsat data, and then we collect all the inputs that will be used by the classifier for the prediction. So for each example, we now have the reflectance in the red, green, blue. We have the NDVI value and DWI value and DBI values. All these are the inputs that are used by the classifier. In addition to that, we have the class, and this is what we want to predict. And then we can use any machine learning approach that we want, because we have our training examples. We experimented with different supervised image classification classifiers. I will not get into all these details, but we found that random forest classifier with 20 decision trees resulted in relatively accurate results. So we're using random forest to train a classifier to learn the characteristics of a built-up and a non-built-up pixels based on all these inputs that we collected from Landsat. After we train the classifier, now we want to predict the class of every pixel in a given hexagon. The output of a random forest is a posterior probability. What is the probability that a given pixel is built up? Now the question, let's say a pixel, the probability that a given pixel is built up is 30%. Another pixel, it will be 50%. How do we determine the threshold of this posterior probability to create a binary map of all the urban areas? What is the threshold that need to be determined for this posterior probability? We experimented with different approaches, and we used the Otsu algorithm. Otsu algorithm is a methodology to determine threshold, and by identifying an optimal threshold that maximizes the between class variance. It is used a lot in image segmentation. So we used this Otsu method to determine the threshold of the posterior probability. The posterior probability, and here you can see histograms of different hexagons. The dashed line that you see is the threshold to determine whether a pixel is built up or not built up based on the posterior probability that was predicted by the random forest classifier. So here you can see the result of this exercise. On the left side of the screen, you can see the output, the posterior probability. The values represent the probability a given pixel is built up. And on the right side of the screen, you can see the binary map, the actual map of the built-up areas that were determined according to this Otsu threshold. If the posterior probability is higher than this threshold, the pixel is classified as built up, and this is what you can see here on red. So we applied this method in the entire country or countries, India, US, and Mexico. And when you zoom out, you can see that this method indeed is able to detect the built-up land cover, and you can see the fine boundaries of built-up areas versus rural areas. How do we know whether this approach actually works well? To do that, we created a data set based on visual interpretation. We hired students who labeled thousands of examples as built up or not built up based on high-res RGB data. After collecting all this data, we did some cross-validation procedures, five-fold cross-validation, and we found that this methodology is able to predict whether a pixel is built up or not built up in an accuracy of around 75% to 80%, which may sound to you as low, but it is actually relatively good, also considering the fact that all this workflow, all this methodology is automatic. We do not rely on manual labeling. The only manual labeling that we did was for the validation. And here I just wanted to show you the results of our automatic classification of built-up areas compared to, for example, MODIS classification, one of the classification schemes that is widely used for land cover land use mapping. So you can see that this method is quite effective. We also did some experiments with mapping urbanization densities. We created a fishnet, and for each cell, we calculated the portion of the area in a cell that is urbanized. This allows us to map urbanization densities in the three countries that we focused on. So to summarize, and I know that I did it really fast, but this is because we are running out of time. Urbanization is one of the most fundamental trends of the past 2 centuries. However, its rate and magnitude have not yet been quantified in sharp precision, especially in global scales, because of computational constraints or because the lack of labeled examples. Satellite data are becoming increasingly available at an increased resolution, including daytime imagery and nighttime imagery. What I presented you here is a novel machine learning approach that we are using to map built-up areas at scale. We utilize 2 sources of data, nighttime light data. In this case, I showed you an example with DMSP-OLS, but this procedure can easily be adapted to VIRS data. We collect examples based on the DMSP-OLS data and use these examples for image classification using Landsat 8 imagery as input to the classifier. Importantly, this method overcomes the need for expensive hand-labeled data for supervised classification because it does not require people to hand-label examples or to rely on external sources as reference, as labeled data. And as I mentioned, we at New Light Technologies are leveraging this method to map urbanization processes in different contexts in developing countries. So thank you very much. I provided the link to the paper at the beginning of this presentation. And I also wanted to take this opportunity just to mention that I'm also a guest editor of a special issue in Remote Sensing Journal that is dedicated to the use of nighttime light data, different applications of nighttime light data in remote sensing analysis in different domains. So thank you.
Thank you, Ran. Just to have one question so far from Jan Peter Muller, who's asked, in your urbanization density slide, why is the river channel in the lower left labeled as urban? And also, have you tried applying the 10-meter sentinel to?
Yeah, so this was just a basic exercise to see whether we can also extract from this data population density. It was just as an exercise, as proof of concept that to show that we can actually detect density. We did not validate it with other data sets or other data sources.
Perfect. And Dana Krill has asked, are you able to use the posterior density values to infer urban density for a given pixel and get values of urban density at sub-pixel resolution?
Yes, yeah, we actually also evaluated this procedure, but there is a debate in the literature whether posterior probability can actually map density. There's no consensus that there's a correlation between posterior probability and density. So, yeah.
All right. Perfect. Yeah, one more question. Mark has said, I noticed the true negative rate was much higher than the true positive rate. Any comment on the pros and cons of that?
So this is why we use the balanced accuracy rate, which averages the TPR and TNR.
Okay, perfect.
And this also due to the number of labeled examples that we had in each category. We were limited by the characteristics of the labeled examples that we were able to use for the validation.
Yeah, that makes sense. Perfect. Now it's really good to see like how sophisticated like your work is. That's really good. And I think that's all the questions we have. So with that, thank you very much, Ran, for joining us.
Thank you.
Great to have you, and it also means we have reached the end. So thank you very much again to everyone who presented, everyone who attended, and especially those who asked questions as well. It's great to have like some engagement back and forth. So yeah, I hope everyone found this informative. I know I certainly did, and hopefully we all got something out of it, and it won't be the last time we run an event like this, and maybe even in person next time. How good would that be? On the screen, you have my email address, you have Tom's email address, and just ways to get in touch in case you have any questions about the workshop, comments about the workshop, comments about our upcoming data set, stuff like that, whatever you think. So yeah, thanks very much everyone, and hope to see you again soon.